We're going to begin this morning talking about with an introduction to NCAR's HPC resources, presented by Irfan Ilahi, who's going to give us kind of the context of NWSC3, which is the project name under which Derecho was introduced, and how Derecho fits into the larger HPC ecosystem here at NCAR. After that, we'll be hearing from Michael Kircher, the operations manager at the NCAR Wyoming Supercomputing Center, to talk about the supporting infrastructure and activities that were required to site Derecho. And then we'll follow that with a presentation by Dave Hart, who's going to discuss Derecho resource allocations and the process for gaining initial allocations on the machine and moving over from Cheyenne. Before I go any further, let me introduce myself. I am Ben Kirk, and I lead the consulting services group. You're going to hear from both me and also a number of my consultants this afternoon, or after our later morning break. We were also happy to hear from a couple of our system administrator staff as well today, Jared Baker and John Bloss, who are going to be presenting details about the hardware technology and job scheduling as implemented in Derecho. So a lot of voices today. You're going to hopefully keep it somewhat interesting until we go into lunch, and then we'll regroup in this room and also virtually after lunch for a hands-on troubleshooting porting session.
So thank you, Ben, and I hope you all can hear me. Good morning and welcome to the Derecho Roadshow. My name is Irfan Ilahi, and I'm the director of the High Performance Computing Division. My division includes the Consulting Services Group, which is managed by Ben Kirk, and also Bill Anderson, who manages the HPC Systems Group. So that group is also in my division. And also the Cheyenne operations section, which is managed by Michael Kircher. And Michael will be talking after me and going through some of the facility work that he and his team has done to prepare for Derecho. Now, the HPC division also manages the procurement, the commissioning, operation, and decommission of all the HPC compute, storage, and tape archive resources. We also manage all of the network that connect all of these HPC ecosystems together. And my division also manages the diversity, education, and outreach for CISL. So we are planning to have a series of these road shows, and our plan is to continue with the hybrid approach where possible. So more and more folks can join in remotely, especially some of our users may not be able to travel to Colorado. So we want to make sure we can reach all the folks, especially the university users as well. As you know, this session is being recorded. So we do plan to create video and share that video as a training and educational resource for our user community. So our aim basically is to improve the content of the roadshow, along with making sure that you have all the necessary information to transition from Cheyenne to Derecho, but we would also like to improve the content. So if you have any feedback, please do not hesitate to provide us feedback so we can make this more user-centric. So, and also please pass the word along, because a lot of your friends and colleagues may not be able to attend, so they can, either sign up for the next one, or when we post this video online, they can go there and be able to take advantage of it. So again, thank you all for your time for coming to this roadshow. Next slide, please. So as many of you know, that the delivery of Derecho was delayed by almost 18 months. The pandemic, the COVID-19 pandemic, global supply chain because of chip shortages, definitely plagued the delivery of Derecho, but there were also some other issues, mainly because of pandemic and supply chain, is that there were a lot of orders from the Department of Defense. It's called DPAS, Defense Priority Allocation System, which means that they can take, if we have delivery already in the pipeline, they can take that and divert that delivery to a defense or any national security associated agency that has a requirement for it. So twice we were bumped off, and that was kind of the main reason for the delay. Now, anyway, we kind of worked through all of those issues, and then we received the hardware in early January. And during the first quarter of January, the project team was very busy installing the hardware and software stack on the new supercomputer. And then during the second quarter, my team and HP subject matter expert worked through several myriad challenges involving hardware, software, stack, and bugs, especially with Slingshot and the Lustre file system. And then we started ATP, or the acceptance test phase, on March 29th. And then even during the ATP, we did some resiliency and functional tests, and we found some issues because we powered the system 3 times all the way to EPO and then brought it back up, and we encountered several hardware and configuration issues. Now, CISL engineers work through these issues, often putting late nights and weekends. And one of the reasons why the system appears stable and we have not seen as many issues, at least that's my observation, as other sites have the exact same system, is because we spent a lot of time during ATP making sure that all the kinks have been ironed out. So knock on wood, I hope that the system continues to be stable, but I think some of the hard work that my team put in paid off. Now, while the ATP was running in parallel, Rory, Brian, and rest of the consulting team, they worked on Gust as well as Derecho for application preparedness, and also deploying the software stack, making sure that the user environment is in place. And then Rory also ran benchmarks, the NWSC3 benchmark suite. And that was because as part of the procurement contract, we have a stipulation that the new system will be 3.5 times the performance, the capability of Cheyenne, which is CSEP, Cheyenne Sustainable Equivalent Performance. And we were able to achieve more than that. And then the system had to run through 30 days of availability tests, which means that our workload would be able to run and the system would not crash, the file system would not go down, and we would not have major issues with the system. So once we cleared those hurdles, we were able to accept the machine. And then in June, we opened Derecho for the Accelerated Science Discovery projects. And the Accelerated Science Discovery project helped us, again, iron out some minor bugs with the user environment. And they were able to successfully go through many of their projects. Some of them are still running, and hopefully they'll move to Casper, which is our data analysis and visualization system for post-processing. But we wanted to allow AST for 2 months, and at the end of that 2 months, we decided to open Derecho for all of our user community. So on August 9th, Derecho was open to the rest of the user community, and many of you have already begun transitioning your work from Cheyenne. Now, Cheyenne will be kept online until December of 2023, and the idea is to make sure that you remain productive while you're transitioning to the new system, because there's always some issues, challenges with getting your code compiled and ready on the new system. But I will encourage you that, remember, Cheyenne is 7 years old. So if you can transition to Derecho, we will help you. If you need any resources, reach out to consultants, reach out to us, and we will work with you to make sure that you can transition to the new system seamlessly. Next slide, please. So before we go a little bit more into detail what our plans are for enhancing and augmenting some of the resources, I just wanted to kind of give you a little bit side-by-side comparison and also give you a holistic picture of the HPC ecosystem at NCAR. So we have a number of clusters, but the 2 main supercomputers that we currently have on the floor is Cheyenne and Derecho. So Cheyenne is a 5.34 petaflop HPC system that was originally built by SGI, and it was released in production in January of 2017. We actually accepted it in December. So we are now in the 7th year of its operation. The hardware is already more than 7 years old. Then Cheyenne features about 145,152 Xeon Broadwell processors. These are dual socket. So we have 4,032 sockets, 36 cores per node, and the total memory on Cheyenne is 313 terabyte. Now compare that to the new system. Derecho will have 2,488 AMD Milan Each one of these are 128 cores per socket. So basically, you're getting double even though you have half the nodes, you're getting more than double the number of sockets, the cores that are there. In addition to the Milans, you also have 82 nodes that have single Milan host, but 4 Ampere 100 NVIDIA GPUs. Now, Derecho is a Cray EX cluster. Now, HPE acquired both SGI and Cray, so we are dealing with our HPE, but this originally used to be a Cray system, and it's about 19.87 petaflop. So it will, as I mentioned before, deliver 3.5 times the throughput of Cheyenne. In addition to Derecho and Cheyenne, we also have a couple of test systems, Laramie, which is the test system for Cheyenne, and then Gust, which is the test system for Derecho. But we also have a data analysis and visualization cluster, which is called Casper. And Casper has a mixed architecture in terms of the node types. It also has 2 different in the network. We have the Ethernet, which is on our Bifrost Ethernet backbone, but we also have the EDR FAT3 on Casper. And Casper is mainly used for data analysis, visualization, small single node jobs, high throughput computing, Jupyter Hub, and also for machine learning and artificial intelligence workload. Now, a lot of the hardware that we have on Casper is getting quite old, so we are planning to decommission them, but before we decommission them, I want to make sure that we replace them with newer hardware that are more powerful and more feature rich, but also not just the hardware. We want to also make sure that the software stack is enhanced and is modernized to meet your requirement. Now, in addition to all of the compute resources, we also have a storage resource. Now, Cheyenne and Derecho each has their high IOPS file system, mainly Scratch. Cheyenne has the IBM Spectrum Scale and DDN storage for Scratch, while Derecho has the HPE cluster E1000, which is based on a Lustre file system. But in addition to the high IOP file system, we also have a large capacity campaign storage, and we are close to 120 petabyte right now on them. They're all IBM Spectrum Scale or GPFS, as it was known formerly, and DDN storage. These are much more stable than commodity, but obviously a little bit costly. Now, we also have a tape library system, which is called Quasar, and you can see the picture at the bottom right. We use that for data collection, but we also use it for disaster recovery. And our plan is to see how we can use the tape library to extend campaign storage. And I'll talk about that in more details later on. In addition to this, we also have an object store, which is mainly used for data collection. And one of our vision is that if we can put our data collection on object store, then when we are ready to burst out to cloud or even utilize cloud, we can put some of this data on the edge of cloud so you can access it with less latency than now. Because one of the challenges of cloud bursting is moving data from on-prem to cloud and then moving it back. We also provide some of the storage to CU because we have a partnership with them. Our scientists are able to access the scientific journals and the scientific data at CU. In return, we provide them about 1 petabyte of storage as a backup and disaster recovery for the CU Peta library. So we use the object store for that. Now, the demand for storage, is growing significantly. Our users are constantly asking for more and more storage. But unfortunately, my budget has stayed stagnant. So we've been looking at innovative ways to see how we can get more capacity by implementing HSM or high hierarchical storage management so that the campaign storage tier can be extended utilizing the tape library. And I'll share more detail later on. Next slide, please. So this is something that, was just out for my curiosity. So I put this together. I just wanted to see side by side how Cheyenne compared to Derecho. I'm not going to spend a lot of time. You have slides and you can kind of look at it. And if you see any mistakes, please reach out to me. But this just gives a really good picture side by side, when you compare Cheyenne with Derecho. Next slide, please. So before I start talking about Casper and other storage augmentation, as well as some planned augmentation on compute, or potentially on Derecho, I wanted to, talk about sustainability and carbon neutral electricity for our high performance computing resources. Personally, this is very important to me, and I've been kind of working on this for quite some time. And we have really good support from management, both NCAR, UCAR, as well as NSF. So I'm very optimistic that we will be able to make significant changes and improvement in this sense. So, I started a few initiatives to improve efficiency along with my teammates. Michael has been very forthcoming and very forward-looking in that sense. And also Ben has been working with the user community to see how we can reduce potential energy usage on our workflows. And then Bill has been working with Altair to see how we can also work with the scheduler so we can report per job energy utilization and other improvements in the scheduler that might ultimately. But what are we doing at the facility level? Now, as you know, we moved from Boulder to Wyoming in 2011 and 12 when we opened the NWSC Center in 2012. One of the reasons for moving was the Wyoming has a cool, dry climate, so it actually minimizes energy use. Now, we also like to use the waste heat that is generated from the supercomputers, and we use that heat to provide building heating, generator block heating, and even reheating of the coils. We do our best to conserve and minimize the biggest losses, like the compressor-based cooling, UPS losses, and the losses from the transformers. Now, making energy efficiency or going towards energy efficiency is not only good environmental policy, it's also good economic sense because it saves us money. So all of the lighting at NWSC has been converted to LED. 10% of the power that we get from our utility provider, Black Hill Energy, comes from our renewable resources. And I'm leading a task force that is evaluating various carbon-free electricity options, including solar, wind, hydroelectric, deep well, geothermal, nuclear, as well as partnership with Air Force Base that's there with Microsoft and other large electricity consumer in that area. And we are also partnering with Black Hills Energy to see if they could provide us 100% cost-effective, carbon neutral or carbon-free electricity. And I'm very, very confident the task force is going to prepare a report in October and present it to the President's Council, the NCAR director, and possibly NSF. And then we'll see how we can get the funding to start either purchasing electricity 100% from a carbon-free grid or having some on-prem generation of our own. Now, there are obviously challenges to all of these options, but I think it's the right thing to do, and we will do our best to kind of see where we get there. Next slide, please. As I mentioned before, we are planning to refresh Casper with new hardware. Hopefully, some of the new equipment will arrive this fiscal year. We've been, again, seeing the same challenges with global supply chain and big demand on GPUs and network switches. In fact, some of the lead time on GPU and network switches can be 12 to 14 months. So it's challenging to get these hardware quickly, but we are doing our best. Now, consulting team under Ben Kirk and Rory and Brian have worked with our user community and compiled a set, technical specifications and requirements. But before they did that, Bill and Ben and I and the rest of the HPCD folks have been conducting market analysis for the last 2 years, mainly to check out the different hardware flavors, the different software that is available out there, the different types of configuration, that is possible. So you know, and as I mentioned, some of the hardware is already 5 years old, and I would not like to keep them much longer. So we have to decommission them soon, but I promise you that we are not going to remove or take away any hardware from Casper until the new hardware is in place. So some of these hardware will continue to be there until they start breaking, because they don't consume as much power. Now, we strongly value your input before we make any of these decisions, and that is why consulting have you know, compiled your feedback. They've conducted various user surveys, had meetings with you at GPU Tiger team, at the NCAR HPC user groups. And I'm also hopeful that we were able to capture enough of your feedback to tackle some of the biggest pain points on Casper. You know, one of the things I heard was that Jupyter Hub login sessions often become oversubscribed, leading to long wait times. And then single core HTC jobs often become memory limited because users were requesting a lot more memory than we're actually using it. So we want to make sure we come up with a better architecture where users are not only kind of educated and provided the resources so they ask for the right memory, but we have separate nodes that are for more memory hungry users, so that GPU nodes do not get bogged down, or HTC or other nodes. So we'll have some dedicated memory nodes. We already have some dedicated memory nodes on Casper, but I'd like to grow that pool. Another thing is that, you know, we don't want to rely on metrics. And that's why the consultant team has been working with you all and other users, because metrics is retrospective. We know what you couldn't do, but what we are really interested in knowing is what is it that you are not doing, or what you are not able to do because we don't have the right hardware or the right software. So that is what we want to determine, that, you know, so that what are the hardware and software limitations on Casper, so that the new hardware does not have those limitations. As part of all of this, we also have to upgrade our HPC Ethernet backbone, which is called Bifrost. And a lot of the work has already started on Bifrost. So you will see some improvement in terms of performance and latency, hopefully. Next slide, please. So in my introduction, I had mentioned that there was going to be some changes in our campaign storage, mainly to extend the capacity and extend the reach, but it will not impact any user who does not want to move to HSM. So if you just want to stay with your current quota, what you have on campaign storage, that's great. But if you wanted something on top of what you have, then you will be able to take advantage of the tape archive tier. HSM, what it allows you to do is basically move your data from spinning storage or hard disk to tape. And it can do it manually or it can do it automatically. Now, the goal of this project mainly is to expand, and the reason for that is the budget constraints. You know, we have to pay for not just the storage, but annually for the file system. And you know, without more money, we just can't buy more storage. So we have to come up with some other innovative way. And HSM is the solution in our opinion. We also kind of have talked to other sites, industry experts, and this seems to be a very reasonable way to extend the capacity. Now we are working on a proof of concept, which we all completed already. And now we have some early users who are using this. And then later this year, we plan to open it up to the rest of the user community. Next slide, please. Now, this is just to basically show you that over the past decade, what the market trend shows. You know, a lot of people think that, hey, the drives are getting very dense. You're getting bigger drives, and the price hasn't increased. That is not true. So between 2016 and 2009 and 2016, the drive capacity actually increased 8 times, but the cost did not decrease proportionally. Then in 2016 to 2022, again, the drive capacity or the density of the drive increased 3 times to 4 times, but the cost absolutely did not decrease in the same ratio. The cost was much less. So we cannot simply, you know, use the same budget and expect expect our capacity to grow, we have to now buy more and more drives, and ultimately bigger storage budget. So that's kind of the driving. So it's not only us, every other center is seeing it. And this basically the chart on the right-hand side shows you the market trend. Next slide, please. So, I had proposed this idea to Anka in 2020, 2021. And after she did thumbs up, the team started working in July, August. We even made a trip to Tucson, Arizona, where IBM has their technology campus and research center for tape technologies. We met with subject matter experts. Now, the reason we chose IBM is we did a market analysis of all the different software and hardware that is available out there. Now, we already owned IBM tape libraries. We already have Spectrum Archive as a software. So it was much more cost effective because Spectrum Archive already has HSM built into it. So it made more sense for us to use IBM. Also, the Spectrum Scale file system is on the tape library, plus it's on campaign storage, and they talk to each other much better than Lustre or some other file system. And since we conducted the proof of concept, we have found no showstopper. Early users have been very happy, no showstoppers. So we are planning to kind of, end of this year or maybe very early next year, open it up to the users. Next slide, please. And now we have the Derecho installation time lapse. So enjoy, please. And if you have any questions after the time lapse, I'll be more than happy to answer it. Ben, you want to kick off the time lapse, please?
Absolutely. Thank you, Irfan. If there's any questions, feel free to pop them in the chat and we'll address after the video. So what you just saw was the final assembly and installation of the racks. Of course, the site preparation for this monster began years in advance. We're going to hear a little bit about that here in just a moment. Michael Kircher is going to be our next speaker in this morning's session. But before we transition to Michael, are there any additional questions for Irfan about any of the goings on here within HPCD CISL? How much did Derecho cost? Irfan, you want to take that one?
Yeah, so this question comes up at all. So the total project, not including any of the facility work and the resources we put in terms of human resource, the total budget was $37 million. And that includes the Derecho, it includes the test system, it includes the storage, the 60 petabyte of Scratch file system or Lustre, and it also includes the test storage file system. But it also includes 5 years of prepaid maintenance and support, which includes parts and labor. And it also included originally one on-site HPE service representative. And the reason we have on-site service representatives, so the response time to repair is much lower. We were able to negotiate as part of the contract negotiation following the delay, even though the delay was not HPE's fault and the contract has a force majeure clause, which means we cannot penalize them, but we were able to negotiate, and in good faith, they gave us significant discount on the 7th year of operation of Cheyenne, and they increased the number of on-site service representatives from 1 to 3. So that's kind of the whole what the project budget got us. If you compare that with some of the other systems, I think it's a pretty good deal, in my opinion.
Thank you very much. Next up, we got Michael Kircher, please.
Hello, everyone. Hopefully everybody can hear me okay. My name's Michael Kircher. I'm the operations manager at the NCAR Wyoming Supercomputing Center. I'm just going to briefly kind of touch on the project that it took to prepare the NSF large facility for this HPC system. So this first slide is going to kind of show the different power steps throughout the years that we've taken as we've gained more systems. And as you can see, each time we have a large peak when we have the overlap of the systems as we transition to our new HPC. For this deployment, we topped out at about 4.3 megawatts at the end. Hopefully we'll be riding that out through the end of the year. And after that, we'll transition fully just to managing Derecho, and we'll probably be floating around 2.8 to 3 megawatts for our facility. Some of the system power requirements for Derecho, this is a very large, dense system. So we had 3,350 amp 40 volt circuits. We had some circuits for the CDUs. Those CDUs are on UPS to make sure that we can constantly cool the system for a total of about 2.32 megawatts for the compute and 60 kW for the storage. Our system cooling requirements, we needed to supply 6 4-inch 65-degree chilled water supply and return connections, a few connections for our cracks, a total of 366,000 BTUs per hour is how much heat this produces. And our flow rates range between 650 and 800 gallons per minute to properly evacuate that heat from the system. The system is incredibly dense, so we're pushing almost a little over 100,000 pounds and approximately 800 square feet for the compute racks. And then the storage is about 10,000 pounds, a little over 10,000 pounds and 225 square feet. The hardware components, Irfan touched on a lot of this in past slides, but the important thing that I like to note is there is a little over 5.5 miles of network cable installed for this system. So kind of some of the 4 major initiatives that we have to go through as we prepare for these large HPC systems is we kind of first have to forecast the future loads. This happens usually 2 to 3 years before the HPC deployment, where we really don't know the exact system that we're getting. The NWC3 initial load forecasted were about 2 to 4 additional megawatts for our site. Currently, Our HPC power source in module B had about 1.7 megawatts availability. So this kind of forced us to have to build out our second module for Derecho. The capacity construction then kind of follows from that. That's a large block loads for mechanical and electrical components. But this supports multiple generations of HPC systems. So through the capacity construction for Derecho, we needed to do some additional piping and fit out work for our Module A computer room, but we also had to add a 3 megawatt transformer, and you'll see pictures of that later. After following our capacity construction, we move into fit up. So that's when we know the specific system that we're going to get, and we can actually design and get installed the components needed to support this mechanically and electrically for the HPC system that gets awarded. We constantly try to, reuse these facility components that we install. Again, they last for, maybe up to 20, 30 years on some of these panels and piping and everything. So we really try to reuse as much of that infrastructure as we can. Fortunately, we were able to use some of the actual infrastructure from Yellowstone, our first supercomputer at the NWC. We were able to reuse a lot of the electrical infrastructure for that to support a lot of the new storage that came in with the Derecho systems. And then lastly, we have some planned outages, for utility level alterations, and a lot of this is focused around safety concerns for personnel working on the construction of the facility. So to show you guys some pictures of some of the capacity construction that we needed to do from the mechanical side. This is some of the pictures of the 18-inch piping header that we had to install into Module A. You can see this is large welded pipe. We have a lot of instrumentation on this, flow meters, differential pressures, so we can measure the flow rates and understand the pressure to help control the pump to make the facility more efficient from a mechanical perspective. You can also see that we insulate all this pipe 65 degrees. We don't necessarily condensate, but we're trying to mitigate risk in case in the future we ever have to lower our chilled water temperature. We have everything insulated already, and we don't have to worry about any of that condensation. The main capacity augmentation that we made electrically was the 25,000 pound 3 megawatt transformer. So this transformer is taking our 24,900 volts and transforming it to the 480 volts that we then feed to the compute nodes. All of this is managed by our facility staff. So we're intimately in tune and understand how all of our medium voltage systems work, as well as the 480 volt that's feeding the computer. Again, Irfan was talking about efficiencies and trying to reduce loss. So if we can get the compute nodes to operate at a higher voltage, that's less transformers that I need to install to get that voltage to the right place. All those transformers create a little bit of loss, so we can limit the loss and make the facility more efficient by having these higher voltage racks. After that, we started our fit up construction. So that has to be handled kind of in a design build, since we're kind of fitting up the facility as the system is getting manufactured and procured by the HPC vendor. So Saunders Construction won that procurement in May of 21. RMH Engineering was partnered to design the system, and then Encore Electric and Murphy Mechanical are subcontract partners, but everybody is kind of working together to procure the right components so we could get them in time, as well as get that designed all in kind of the same track. So everything kind of moves in parallel through the fit up. It's a pretty chaotic time for the facility. We use all the requirements based on the machine unit specifications provided by the vendor, and then RMH creates construction documents while all of our contractors are participating in that design. The construction starts and then completes, and then the Derecho delivery happened, and then the final infrastructure connections are made to the system. So kind of to just touch on some of our fit up construction that we did. On the left side, you can see these are all the pin and sleeve receptacles that we installed for the new storage system that came with the Derecho. We also installed our 480 volt distribution and branch circuits. And then because these systems have such large, these 150 amp 480 volt circuits that are feeding each of the compute racks, there's only one manufacturer in the entire world that makes a pin and sleeve connector for that. The lead times were incredibly long, and you have a pretty large single source of failure when you come to that. So we actually were able to come up with a different way to connect the compute racks, where they are now wired directly to fuse cabinets. So we verified with HPE that if they ever need to work on the primary voltage side of the rack, that all power needs to be removed. So that way we could tie all of the whips into one fuse distribution panel, and then we were able to actually feed those directly through the fuses. That's also plays into some of our safety things that we like to heavily rely on. So fuses actually trip faster than a breaker, so we're actually able to minimize the arc flash potential that can happen if a technician is having to do voltage checks or something like that, just to limit the danger around some of this high density, high draw equipment. Some of the mechanical fit up work that we did, we installed some crack units. The Derecho HPC system rejects 95% of its heat directly to water, but there is 5% created by the CDUs and some of the login nodes, the river racks that create heat that goes directly to the ambient air. So we use cracks to try to pick up that extra heat, and then everything else goes directly to our hydronic systems. So the middle picture, you can see some of those complex CDU line sets. We have to make sure we have flow control in there, so we get the exact right amount of flow going to those, so we can balance the system properly. And then also we have to make sure that we're having water and power mixed underneath our floor. We have to make sure that the layout is very specific, so that way we don't have any connections over an electrical panel to try to reduce any kind of safety issues. Finally, you can see on the right, some of our crack line sets that were installed for that air load. And then finally, I just want to touch on some of the outages. My team is working, with Derecho, we were working about 24 months ahead of time to try to prepare for the system, but we want to limit the impact to users as much as possible. So we ended up doing a total of 10 shutdowns during the project. 5 of them were considered small shutdowns. So this is for single or multiple branch circuits. This is no impact to the computer room or the operations. The medium shutdowns, these are larger block loads that can potentially impact computer room operations, but most of the time they don't. We were kind of modifying our essential power modifications for some mechanical redundancy, so that way we can increase our uptime. We augmented our essential UPS power modifications. That's used for networking equipment at the NWC, and then our mechanical equipment startup and commissioning kind of falls into this medium shutdown. And then finally, we had one large shutdown where we have to shut down the entire computer room. That was July 26th through July 30th, 2021. We had to alter our medium voltage systems. Our computer room UPS systems needed to be altered. And then we had some mechanical power alterations as well. We kind of rounded that out with some commissioning activities just to make sure that we could guarantee that we could manage both systems at the same time before we brought anything back up. So here's some pictures from our large shutdown. You can see in the top left, some workers are pulling in some of that medium voltage 24/9 cable. I don't know if any of you've seen or experienced anything with medium voltage cable, but it's built a lot like a coax. So there's a lot of insulation around a solid copper core just because of the induction that can happen at these high voltages. We have to be very careful. They have to be properly high potted and tested on all connections as well. That kind of falls up to the top middle when we had to get into our vaults, and we have to use air purifying machines to make sure that the workers are safe. And then on the right side, you can see that's where they're still pulling on that medium voltage cable, but all of our medium voltage gear has to be open, so we don't want to expose any of them to that live voltage. So that's why we have to do some of these shutdowns. The bottom are kind of our UPS alterations, and those are the same thing. We have to get into some vaults inside of our facility, but that we don't want people working around live exposed electrical gear, so we have to shut all that off as well to make sure that they can pull the cable safely and get everything terminated. Finally, I just wanted to kind of throw out some QR codes from our build outs and our virtual tour. Our visitor center has been updated since this is done, so we're going to try to get this refreshed this year. But thank you very much for your time.
Thank you, Michael. Are there any questions either online or in the room? So after some responsible shutdowns during the COVID era, you guys are open for tours again, right? Is that correct?
Yes, that is correct.
Awesome. Encourage anyone who hasn't seen the facility, if you're in the area, make it a priority. It's a good thing, and they love showing it off. It's an impressive facility. So next, we're going to hear from Dave Hart, who's going to talk about allocations on Derecho, and in particular, moving from Cheyenne, if that's of interest to you. And then we will take a morning break. Thank you, Dave.
Hi there. Thanks for having me. I just want to go through some of the changes we've made now that Derecho is live and open to all users. Oops. There we go. So yeah, Derecho's got a lot of stuff to allocate. 2.7 billion core hours are what we produce, what Derecho produces in a year. And almost 2.75 million GPU hours. So this is the breakdown of the usage or the intended usage of the system according to the primary user facilities we support on the system, with the university folks getting nearly 1 billion core hours per year and 1 million GPU hours. NCAR researchers have about 825 million core hours to spend, as well as 850,000 GPU hours. The CESM community, over 450 million core hours. University of Wyoming, about 350 million core hours, and the AMPS, the Antarctic Mesoscale Prediction System, they have about a 50 million core hour allocation to work with. And just a fun fact, if you divide the rough core hours by 1,000, that's how many GPU hours the system has according to each facility. It's about a factor of 1,000 just by sheer coincidence, but it works out nicely for round numbers. For university community, can't see my headings here. Hold on, there we go. So for university community allocations, the small scale allocations remain the same, but we have increased the amount of resources available for each of those opportunities. The small awards still require NSF funding, but you can get up to 1 million core hours for having such an award, or 2.5 thousand GPU hours. You can also double that with a one-time supplement to wrap up your work at that small level. Exploratory, which is unfunded work, including dissertations by grad students. That's those are primarily used for, but they're also open to new faculty who haven't computed here before. You can get 500,000 core hours or 1,500 GPU hours plus a one-time supplement again, so up to 1 million core hours to do your dissertation or in similar work. Classroom allocations remain available, and now they're putting all this on Derecho as well, with the same limits as exploratory projects. There are no funding constraints. That's all open to any instructor at any institution in the US. Data analysis is another allocation we offer, but does not require or allow Derecho access, but it does require you have a plan to analyze NCAR hosted data sets. So this could be any funding source as well. On the large scale side, the university allocations require an NSF funding award. They would be for more than 2 million core hours, because obviously you can get up to 2 million with a small request, or 5,000 GPU hours. These are reviewed twice annually by the CISL HPC allocation panel, or CHAP. The next deadline for proposals is September 12th. So if you're interested, now's the time. The panel will meet in October to review those proposals. So again, that's the important deadline coming up for the large scale requests. And remember, we have almost 1 billion core hours a year to allocate. So think big if you're considering one of these proposals. And again, just a reminder, for all university allocations, you must have a US-based project lead. It should be an academic or nonprofit institutional affiliation for the project lead, and it must be work in the earth system sciences or related fields. I've mentioned that it requires an NSF award, but it does not have to be in the geosciences. It could be from the SCISL directorate, from social science, any NSF directorate, as long as the work has a relationship to the earth system sciences. So, did I skip one? I don't think so. So for NCAR labs and projects, there are 4 types of allocation. I want to spend a little bit more time there for the folks who from NCAR. The NCAR strategic capability projects are the equivalent of what the CHAP reviewed awards are for the university folks. These are large scale projects, too large for the lab blocks, and it comprises about 60% of the NCAR portion, or almost 500 million core hours a year is what we've targeted for those, and about 500,000 GPU hours. The labs themselves, they get block allocations that are managed by the labs themselves. And that's about 260 million core hours per year. The labs handle that. We support them in how they want to manage those projects. There is a director's reserve that's handled by Everett. And now a new thing that's we're working on for Derecho are these external funded projects. They're going to be handled somewhat separately from both NSC and the lab grants, and should benefit the labs that rely on a lot of external funding. And more rules on that and details are coming soon. I have another slide that talks a little bit more about that as well. The lab allocations are probably most familiar to everybody. All the labs get a certain amount of time on the system. The table is shown here. All the labs have more core hours than they did with Cheyenne, and that's not including the performance boost that you get from the Derecho hardware. The HAO and RAL got a somewhat lower amounts due to their expected use of that external projects option I just mentioned to support their work. And the NSC threshold remains at 10 million core hours or 10,000 GPU hours, give or take. There's always some flexibility there for projects that have a challenge with using the lab block grants or fitting within those lab block grants. So again, I wanted to touch on these external project allocations. These final details are being ironed out, so stay tuned. But the short version here is the projects that have non-base funding awards for NCAR. They have the ability to ask for a project that is separate from their lab block allocation that has a set allocation for the life of the award, very similar to how the university projects work. So it doesn't impose on the lab block grants. It may be reviewed by the NSC panel, but it will still be deemed strategically meritorious, although the plan has to be up to snuff with the justification, and it'll be verified by the panel. If you have an externally funded award and it's fairly small use of the system, it can be absorbed by the block allocation if that's the way you prefer to handle it, or it could be handled as an external award as well. The intent with all of this, and again, we'll get through all the details at a later date when they're all finalized, but overall, the intent is to better align with language that's actually in the cooperative agreement for NCAR. So what we're trying to do is comply with how the cooperative agreement wants us to deal with non-base funding awards. Now, just a quick wrap up about migrating your allocations to Derecho if you already have them. So for NCAR researchers, the labs have been given their Derecho allocations, no actions needed, you're good to go. You can continue using your Cheyenne allocation or your Derecho allocation. You have both available to you. For the NSC projects, the large scale projects, if you want to move any of your Cheyenne core hours to Derecho, the project lead or the project admin needs to follow these steps. Go to the ARC portal, select allocations, find your project, and select transfer from the actions menu. For university projects, that's the same set of steps you'll want to follow as well. You can transfer Cheyenne core hours to Derecho for all your university projects, whether it's a small or a large. If you request a transfer on a small allocation, we're actually bumping you up to the full million just to save us time in the future in case you ultimately want that amount. I should say a couple words here. If you need Derecho GPU hours, because the resources are so substantially different, and there's at this time very few use cases where hybrid jobs are being run across the non-GPU and the GPU nodes, we're allocating the system effectively as if it were two systems. There's the AMD portion of Derecho, and then there's the NVIDIA portion of Derecho. In the allocation request system, you'll see Derecho GPU and Derecho allocations. If you want to use the GPUs, you follow all these same steps. You'll want to ask for a supplement because obviously there's nothing to transfer to your project, but we'll entertain those requests as well. And if you, as a CHAP request or an NSC request, you'll be asking for those amounts of resources separately. And it's just to help manage them. There's many fewer of those nodes, so we want to make sure people who are using the GPUs need them and will take advantage of them with their codes. If you have any problems with this transfer, just put in a help ticket. We'll get you sorted out, right? Our goal is to get you there as quickly as possible. If in the next couple months you do need to, you can welcome to continue using allocations on Cheyenne. We are not making any more formal allocations there, but if you're desperate to finish up something, we can entertain some requests, put in a help ticket. You won't be able to do that via the allocations process, but if you do need some more Cheyenne time, let us know. We can discuss it, make sure that's the right fit, and then handle it via a ticket. And I think those were all of my slides. And I got a couple of questions. David, John, does he need a mic, Ben?
One question I have about the GPU charging.
Sure.
So if we ask for one GPU node for an hour on Derecho, does that charge one GPU hour or 4 GPU hours?
I believe we have it sorted out we'll charge for the full node, correct? So on Derecho, it's the full node. If you want a single GPU, go to Casper. That's a better fit for single GPU jobs.
Okay, so but it would be charged for 4 hours.
4 hours, yes. All the GPUs for the hour. Yeah, all
Okay.
4. So yeah. Good point. Thanks, David John. Was there another question or is it the same question?
So just so I'm clear, if in the future I want to use both the CPU side and the GPU side,
Yes.
I should just get in touch with you. We don't have anything planned yet, but like have some ideas of where that we might be able to leverage that.
Sure.
But that would probably be like very large scale.
Yes, and if you do need to run hybrid, a single job across both partitions, just make sure you have allocations on both and the job will run.
I'll just mention for the benefit of the audience online too, we have a lot of account automation that's tied to your allocation. So if you're wondering why you can't log into Derecho, when we give you the URL a little bit later, it could be because you don't have an active allocation. So that's really the first step in getting your user account set up. We're going to start back up here in just a moment. I'd like to introduce our next speaker of the morning. First, we're going to hear from Jared Baker, who's going to talk to us about the Derecho architecture and technology, primarily from a hardware perspective. Jared is a member of HSG, our High Performance Computing Systems Group, and is one of the lead administrators on Derecho from a hardware perspective. After that, we'll hear from John Bloss, who's going to give us some details on the scheduling implementation on Derecho, with emphasis on how it is similar, but also different in some areas than Cheyenne.
Good morning, everybody. As Ben mentioned, my name is Jared. I'm one of the lead system engineers here at NCAR for HPC deployments, and one of my projects has been Derecho over the last couple of years. So with that, we're going to go into a hardware and technology deep dive of the core system components. So next slide, please. So overall, here is a picture schematic of a rack and how they're laid out with the different components. So you can see switchblades, chassis, cooling distribution units, compute nodes, and manifolds, all how they somewhat fit together. But all in all, the complete proposal from HPE Cray ended up being about 19.87 petaflops, and that included both HPC and a parallel file system. We do have a parallel file system is 60 petabytes of usable space on Lustre, which is different from what was available on Cheyenne as well. So the CSEP, which is the Cheyenne Sustained Equivalent Performance, exceeds the RFP requirements that we came in at 3.51. But what's different with Derecho, as many of you know, is that there's a sizable GPU component on this. So this is a fairly large installation base, and it does also include 3 full-time engineers from HPE as well to support hardware fixes, remediations, and such. Next slide, please. So just want to talk a little bit about the 2 different blades that we have. We have both AMD CPU blades and then GPU blades. Both have AMD EPYC processors. But the difference here being that there are 4 nodes per blade and then 64 blades per cabinet on the CPU side with a single slingshot 200 gigabit injection point. And then the GPU side, we have 4 injection points and only 2 nodes per blade, but you have 4 GPUs per node on that are all interconnected with NVLink. So a large portion of the flops definitely come from the GPUs as well. So next slide, please. Again, more anatomy of the blade. You can see all the water cooling that goes on within these systems as they are very dense. So you can see the copper blocks that sit on top of all the CPUs, and we even water cool the DIMMs and IBOC controllers as well. So in each, like I mentioned earlier, each blade holds 4 liquid cooled nodes, each with the Zen 3 Milan processors that have 64 cores and 128 threads per socket. And then we use 16 DIMMs for a total of 256 gigabytes of RAM per node, and then 1 200 gigabit per second Cassini Slingshot 11 network point. So in this system, we're using HPE Cray proprietary interconnect rather than InfiniBand like that was used in the two previous systems, Yellowstone and Cheyenne. Next slide, please. Just different look at a different node. This is a GPU node. You can see off to the left of the slide where the GPUs are all located with the same water cooling system that we have. The difference on the GPU nodes is there's only one AMD EPYC processor with 64 cores and 128 threads, but they have double the memory, so 512 gigabytes of memory in them. And then each of the NVIDIA A100 GPUs has 40 gigabytes of VRAM on them. And then to facilitate the communications with the GPUs, we have 4 200 gigabit per second Slingshot 11 network interfaces. So gives you nice communications patterns between different GPUs at scale. So next slide, please. Let's see, Slingshot overview. Again, the chassis are composed of 8 physical blades with 4 nodes per switch blade, and then each chassis has 2 Slingshot switches, at least in the CPU racks. In the GPU racks, there's actually 4 Slingshot switches that facilitate all the network communications and connections. The blades for compute nodes are all mounted vertically from the front, and switches are horizontal. That allows a nice orthogonal made up on the connections in the back plane. So next slide, please. And then, so a little bit about the network. Derecho is a Slingshot Dragonfly topology, so very different than the Hypercube that is used on Cheyenne. You can see a nice graph here of the different, what they call switch groups. So each cabinet is effectively a switch group with the exception of GPU nodes. That cabinet is actually 2 switch groups itself because there are so many connections to the individual GPU nodes. But what's unique about this Dragonfly topology is that it's a 3-hop maximum to any component. And then there are 3 different types of connections that are used. There is an edge connection, and you can consider these the local type connections to your edge devices. So compute nodes, login servers, stuff like that. And then there's what they call local connections, which are actually connections within the switch group. So that, if you were to equate it, this would kind of be like your local neighborhood connections. And then we have global connections, and these are all at the global scale, these are all active optical connections, but these would be interstate style cables, so how you get to other switch groups on your communications path. But like I said, what's nice is that this is a very well connected network with 3 hops max to anything. It also includes adaptive routing and congestion control as well, that we've seen work at this point. So we have inside of Derecho, there are 13 switch groups. Like I said, one switch group for our river rack. So this is login nodes, our Arista router connectivity, which we'll talk about in a minute, PBS servers, and connections to the ultimately the Lustre file system. And then 10 switch groups for the CPU racks and 2 for the single GPU rack that we have. Next slide, please. So as I mentioned, the HPE Cray solution included a parallel file system. It is comprised of 6 ClusterStor E1000 systems and gives us a total capacity of 60 petabytes of usable space. And we can double this in our capacity size for the future if required. We are all set up from a network perspective to be able to take advantage of that if the time comes. And then they did meet our requirements by providing 300 gigabytes per second of aggregate IO bandwidth across things. And all of these subsystems combined, there's just over 5,000 16 terabyte hard drives. And then for because this is Lustre, the metadata is segmented away, similar to how GPFS sort of does it, but we have individual metadata servers, and we use 40 terabyte SSDs for those. And then we have 2 metadata management units with 4 metadata targets. with one metadata target exported per MDS. Basically, what this is ultimately saying is that we have highly available metadata system for the Lustre file system. And again, it's based on a Cray version of the Lustre parallel file system, so just a little bit different than your normal Lustre file system that you would find in the open source community. A little bit of extra vendor value add there. Next slide, please. And this is just a little bit of a graph of performance. We are still working on tweezing out a little performance for sustained throughput, but we were definitely able to hit the 300 gigabyte per second bandwidth requirements for both reads and writes. You can definitely see that we can have very high peak writes and some very good reads. Next slide, please. So how do we integrate Derecho into the overall NCAR HPC environment itself? So off to the left, we have, the Derecho production HPC system, and it talks, a little bit about everything. But what you should realize is that everything in the Derecho HPC system is ultimately connected to the Slingshot fabric. And then we utilize some Arista 400 gigabit switches that we use as edge routers. We tie them together with an MLAG connection for high availability. And then we link the Cray Lustre storage system directly to those Aristas so that you have a very short hop to scratch space. But we also tie the Aristas directly into the NCAR Bifrost network, which was done a few years ago. And that's the HPC backbone at NCAR. So what facilitates that is Glade and Campaign Store are connected to Bifrost, as well as Casper. The internet for HPC purposes definitely comes through the Bifrost links. And we've worked really hard to making sure that basically anything that we need to network anymore and going through in the future is capable of being put on that network. So the different systems can all communicate efficiently with each other and whatnot. So next slide. And just one change that we've made different from the Cheyenne mechanism is that we're using a series of network address translation gateways, so you can get outbound internet access from all the nodes, but we will not be providing inbound access. So you'll have no ability to SSH directly to your compute nodes, similar how do you do that on Casper. But you will have outbound access so that you can do things like talk to GitHub or other sites for gathering code at runtime and such. It also allows you to fetch small data sets at runtime as necessary. But if you are doing large data transfers, we still prefer you to use the data transfer mechanisms that we have in place, like Globus. Okay, next slide. So a little bit about the login environment and scheduler infrastructure. We have 6 CPU-based login nodes that will be served in a round-robin type fashion. Each of those will be connected with a 200 gigabyte Bifrost connection, as well as a Slingshot connection. And then we have 2 GPU login nodes, and we're going to serve those up basically the same way. The difference is that they have a A100 PCI-based GPU if your codes require, a GPU to compile for the appropriate compute capability and such. One large difference that we will talk to, and I know Ben Kirk will cover a little bit more, is that we are using control groups. That is a Linux feature in the kernel to limit the abuse of login nodes. So if you launch heavy processes or memory intensive processes, you will be emailed and throttled in various ways. But we thought that this would be a much better reaction rather than killing all your processes and notifying you afterwards. So it's a little bit of a nicer way to go. Your processes won't be killed, but you might get limited in the amount of CPU cycles that you're able to obtain on login nodes. And then as far as PBS Professional, which is our scheduler, and John Bloss will talk more about later, but we have 2 dedicated PBS workload management systems And we're using an IBM Spectrum Scale file system or GPFS in the background for highly available state directory where the database lies for all the jobs and accounting records and such. And that file system is made up of a RAID 10 like storage with basically high performance SSDs to maximize IOPS of the PBS server. And we're hoping this will help quite a bit with things like queries and overall basically the PBS performance. So hopefully that will be less of a bottleneck in, going forward on the Derecho system. Okay, I believe next slide, but that is off to John at this point. So happy to take any questions at any point. Feel free.
Thank you, Jared. We got at least one question in the room here. And if anyone
Yes,
has any
hi.
online, please feel free to
Yes,
either
hi,
type. Oh, sure. Go ahead. Is there a question online?
this is Natalie from Epic. Oh, I can type it probably.
Go ahead. We got you. We hear you just
Okay.
fine if you want.
My question was about the jobs that may need to have internet access. Do I need to specify separate node or maybe use a login node for doing like compilation and network access?
Nope. If you need internet access, all nodes have that. It's very similar to how your home internet would be set up. Like I said, they're not publicly available, but they do allow you to reach out to places like GitHub or other sites for fetching code.
Okay, just has some errors, but I probably I'll reach out later.
Yeah, feel free to post them in the NHUG Slack channel, and we can definitely look at those.
I already have ticket opened, so whether. Yeah, I'll post them anyway. Thank you.
Oh, happy to help. No, thank you for raising the question.
So you said that direct inbound is not allowed, but can you still SSH from the login node into a compute node? If you
Yes.
want to say debug and stuff?
Yep. So that'll work as long as you have a job on the node, right? You
Okay.
aren't allowed to log into other nodes where you don't have a job, mainly to reduce the amount of jitter associated with, if anybody else is using that node.
Yep, that sounds reasonable. So thank you.
All right. Thank you very much. Thanks, Jared. We appreciate, especially the compute node internet access is a new feature for this scale. We appreciate the effort to get it in place, and we'll certainly monitor to make sure it's behaving as expected over time. Next up is John Bloss, who's going to talk about the scheduler configuration on Derecho.
All right, can everyone hear me? All right, thank you, Jared, for the overview on the hardware associated with Derecho. My name is John Bloss. I am another HPC engineer with the High Performance Computing Group, and I'm mainly in charge of job scheduling and environment surrounding that. So I want to go over a little bit about how the Cheyenne queue structure was set up and kind of draw some parallels between that and the Derecho queue structure. So Cheyenne's queue structure was fairly basic. There was only really 4 queues that users could really take advantage of. And all of these queues were associated with a job priority. And so we would evaluate all the premium queues first, regular jobs, and then economy jobs. So all these queues were standalone. And we also kind of used placement sets for describing node locality requirements, which was a little bit more kind of relevant for Cheyenne with its 9-dimensional hypercube. So with Derecho, we're adding a few new features, and we're hoping to add a few features in the future. So with Derecho, we're using a routing queue based structure. So very similar to Casper, where you just submit it to a main queue, and then the job kind of filters into the appropriate queue based on the resources that you've requested for the job. So, big difference is queues for specific hardware types. So we have both CPU type nodes and also GPU node type nodes. So we really wanted to make sure that, we didn't have any CPU jobs really getting into the GPU queue and utilizing those precious resources that could be better used for GPU specific jobs. Job priority is now a requestable resource. So instead of submitting directly to a priority-based queue like premium, regular, or economy, you're just going to select what kind of priority you'd like your job to have. And tying into that, we're now utilizing a job sort formula. So, one of those formula parameters is the job priority. And so that's taken into consideration along with a few other factors to determine when your job should run in terms of a list of jobs. And then we're also going to be using C groups for effectively sharing node resources. So you can also submit jobs to a develop queue, which would then pop onto nodes that are being shared, but would allow you to run jobs that are only half or maybe a quarter size of the node, if that's what you need for any development purposes. We're also adding the ability for users to take advantage of MPS on the GPU-based resources. So if you need that kind of service, you can now request that similar to the way you do it on Casper. And then we're also adding preemption queues. So these queues are for if you have a job that you don't really care when in the lifetime of the job it actually finishes, maybe you'll get enough work out of it with a good amount of time in the job. But this will allow you to take advantage of some spare cycles where maybe jobs in the main queue aren't using those resources at that time. Eventually, we would like to be able to offer a Luster jobs scratch statistics as part of the job runtime. And so at the end of the job, you would have, as part of the accounting record, a log of, various Luster scratch statistics throughout the course of your job. Power usage for exclusive jobs. We plan to also add that hopefully by the end of the year, but we'll see. And then along with that, being able to select a power profile for your exclusive resource jobs. So say you have a CPU job, but you only want to consume 1200 watts of power on each of those nodes. That would be a option at that point. And then eventually cloud bursting capability for some projects. This will be kind of a pilot, and there's plenty of things that we still need to work out, mainly regarding who's actually going to get charged, because NCAR is not going to provide a credit card for us and for you to cloud burst out to the cloud for infinity. GPU utilization and memory statistics and job records is something we also hope to add at a future point. But then that would also be included in your job records to give you some picture of how you were actually utilizing the GPU resources as part of your job. So this is a high-level overview of the Derecho queue structure. It is quite a bit simpler than the Cheyenne queue structure. And I know you're saying, John, there's way more queues here than what we just saw on Cheyenne. But all those queues that are yellow and red are not ones that you can directly submit to or really see. So the main three queues that you see in green are the ones that you're going to be able to submit to. So if you're doing, regular production work, you're going to be submitting to the main queue. If you want to do some test or development, submit to the develop queue. And then if you want to take advantage of some of the spare cycles on the machine and get like a little bit of work done, you can submit to the preempt queue. And as you can see, also, we are offering hybrid queues. So if you want to have a job where some subset of the resources are CPU nodes and some subset are GPU nodes, you now have that ability. So as I was saying, we have the two primary submission queues, main for all development or production workloads and development for any kind of testing. CPU and GPU nodes are allocated directly to the various queues. And so there's no way for you to get into a CPU queue and be allocated a GPU node or resource. So this was kind of tied into what Dave was talking about with Derecho being effectively two different resources, an AMD resource and then a NVIDIA resource. Access to production GPU queues will require membership in a project that has been granted GPU core hours. So you do need to make sure that you request the GPU resources if you want, GPU resource time if you want to use those GPUs. And then, of course, preemption queues are also provided for both CPU and GPU resources. Again, you will need to have GPU core hours in order to use GPUs, even in the preemption queues. And then, of course, job priority is now a resource flag. So as part of a job submission, you can just specify, a job underscore priority of economy or, premium in order to get a little bit of boost or, have a little bit less charged for your job if you're going for the economy route. By default, any job will get a normal priority assigned to it, and then development and preempt jobs will have 0 priority assigned with those jobs. So a big part of the job priority is that it ties into the job sort formula, which I talked about a few minutes ago. But as you can see with the top point, you can specify a job priority with a additional L flag. So this option is taken into consideration for the job sort formula with the 3 job priorities listed there. So economy is a little bit less priority, but still quite a bit more than preempt or development. Regular is what you get assigned by default if you don't specify anything. And then premium, you get a little bit of a boost, about half a day's worth or so, if you're looking at the formula. So this job sort formula used on Derecho is very similar to how we're doing scheduling on Casper today. So on Casper, we're using a similar kind of job sort formula. The parameters and factors are a little bit different because we have different aims for Casper. But in a sense, the formula takes into consideration job priority, fair share factor, eligible time, and then requested CPUs and GPUs. So on Derecho, we get heavier weight and more job priority towards jobs that are requesting more CPUs or more GPUs. And then job priority is, again, a factor in this where if you're selecting a premium job priority, you will see it go fairly quickly. Economy is kind of equivalent to saying it's all right if it takes, half a day longer as far as the job formula is concerned. I know there was a question last week about, is there any way for me to change the job priority of a job I've already submitted? And my first answer to that was, well, you probably shouldn't do that anyways. The longer answer is it probably won't make too much of a difference too. So if you're submitted originally as an economy job, have already waited a day and say, man, I want this in the premium queue, chances are your job has already accrued enough priority that it wouldn't make a difference if we then switched the job priorities to a premium. because after a day or so, your job priority has already increased enough by eligible time that it really doesn't matter at this point what your job priority is. So touching on multi-process service support for GPUs. So with Derecho, we're offering this as a toggle for your job on the A100 equipped nodes. We already have this on Casper. If you've already tried that out with the V100 or A100 nodes over there. And it's just an additional little selection on your original select line. So, MPS equals 1. So the MPS server and user daemons are created automatically and then torn down at the end of your job. And yeah. So, looking forward to future features that we hope to have on Derecho. We'll have the ability to pull Luster job statistics and report on certain metrics for these so that you can have a better understanding of any issues with performance or operation of the Scratch file system during the duration of your job. So these will include, basic metadata operations and data operations, as you can see from the screen. These metrics will be aggregated by PBS job ID and can be useful for uncovering application performance bottlenecks, including, file system access patterns and excessive, for instance, tempter use by underlying libraries. And so this is hopefully a little taste of what we'll be able to offer at that point. So this is just a Grafana dashboard for a job that we ran on Gust during early testing period. So additionally, we're hoping to add some power monitoring management abilities to PBS. So we're working with HP and Altair to develop a power hook that integrates with this new Cray EX hardware. The hook will report power usage for resources assigned to a job that are used exclusively. And it will be able to eventually set a power profile for the nodes. So again, if you wanted a full CPU job, but only wanted to use like 1,000 watts on each of the nodes because your code, performs better and, you're not going to get much performance past that point, this would be a great option. We also plan to integrate the ability to power down nodes when not being used for jobs and power them up when they're not needed. Hopefully we don't need this feature too much because you all will be using Derecho full bore. But currently, the development and testing is currently taking place on Gust. We're working through a few software issues that we're hoping we'll be able to test sometime in the near future and to validate whether HP has been able to give us some better code for this. So this is just an example of what this would look like in a job. So if you look back at a job, you should be able to see resources used. And this is a cumulative power used for the job itself in kilowatt hours. So additionally, I wanted to touch on, what this would look like on the user-facing tools. And so with QHIST, a tool that Brian Vandervent has put together, we've already adapted it so that it would actually, give you a readout of how much energy you used for each job within the QHIST listing.
So the job sort formula is something we've been using a bit on Casper,
Yes.
But it's new to users coming from Cheyenne, correct?
Mm-hmm.
I guess all of those knobs are somewhat tunable, but also explainable. If you encounter any, bizarre wait times or any, behavior that doesn't make sense to you, certainly reach out to us because, we can, all of those things are somewhat configurable and we'll monitor execution through time. So again, thank you for joining. My name is Ben Kirk. I lead the consulting services group. You're going to hear from a good number of the consultants on the team today. We're going to start by talking about how you first log into Derecho and what's similar and different in terms of our login node environment. Next up, you'll hear about the user software environment. Again, what's similar and different coming from Cheyenne, including the module set, and then talk about file systems and storage spaces on Derecho. So the first thing to note, not just the login environment, but the system itself. I want to start with what's in red here. We do plan to have a monthly maintenance window on the first Tuesday of each month for the foreseeable future. So the first Tuesday is roughly our intent. We may move that on a month-by-month basis with added heads up, of course, depending upon readiness of things like vendor software availability. But as you saw from Jared in the hardware overview, there's a lot of disparate components in the system, and it's a relatively new system still. So we have some known issues, and I'm sure more will come our way that require vendor software patches, and so we need time to install those. So just setting expectations in that regard. Other than that, you log into Derecho very similar to you do Cheyenne. We use SSH. The host name is derecho.hpc.ucar.edu. So that's a difference for those of you coming from Cheyenne. We are intentionally hosting this under the HPC domain name because it gives us a little bit more flexibility in how we manage the domain to IP address mapping and things of this nature. If you log in to Derecho, of course, with your active allocation, as I mentioned in Dave's talk, this will place you on one of 8 login nodes in a round robin fashion. As typical, you'll be sharing this login node with 50 to 100 plus users. So please mind your resource utilization. Typical things you want to accomplish on login nodes are relatively low intensity. So writing text, text editors, interacting with code, compiling smaller programs, right? So, nothing that's going to do a parallel build expecting 40 cores or anything like that. Would direct those into the queues, but small compilation is fine. As is, moderate sized data transfers, and primarily interacting with the job schedulers is the main thing that you usually do on the login nodes, and Derecho is no different. What is different, Jared mentioned this briefly, we are using a program called Arbiter 2. Developed out of the University of Utah, and this allows us to do resource utilization and monitoring in a way that's hopefully gentler to the users than what's currently implemented on Cheyenne or even Casper. The technical approach is that when users log in, your sessions, all of your content is placed within a Linux C group, a control group, which that allows us a mechanism to monitor and then ultimately restrict resource utilization if necessary. The overarching intent is to prevent users from monopolizing the login resources while also not kicking you off for exceeding thresholds. So I'll walk through quickly what that looks like. In case you see any of these emails, you'll know where they're coming from and what to do about it. So again, as typical in a shared HPC environment, the login nodes are the most highly shared component. That, and of course, the parallel file system usually. So we ask that all users be considerate of their resource utilization. Anything that's high intensity should be run through the queue system where you have access to several thousand dedicated nodes as necessary. We're using Arbiter 2. This will detect and restrict excessive resource utilization, and you'll get emails alerting you to what triggered an exceedant event and what's happening. The gist of it is, though, if you exceed a pre-configured CPU threshold, your Linux C group is effectively squeezed. So the first step is we basically ratchet you down to 80% of what your previous consumption had been, and you'll get an email and you'll know what's happening. If this goes on further, it can be restricted even more. But the net benefit is that instead of getting kicked off with an email after the fact, you get an email in real time and your session is still running just at a slightly slower rate. So this is something that I triggered back in May of this year. So I get this helpful email that tells me I violated the usage policy. In this particular case, I had a process called make squash FS that was very happy to take all of the cores in my allocation or in my login allocation and run it for a period of time. So it also includes this helpful graph. You can see in this case that make squash FS bumped above the limit. And so I was throttled down to 80% of my previous CPU allocation. Had this gone on longer, it would have been throttled down even more. But as you can see, the net effect is hopefully that rather than getting abruptly kicked off a node, you're gradually shrunk. And meanwhile, if you don't notice, we also notice in consulting, and we can take action as necessary. If you receive such an email and you feel like you did nothing wrong, first off, you didn't do anything wrong. These are tunable parameters. These limits are reasonable. Let me say that they're reasonable but also configurable. If you are unclear on why your particular process violated any of these thresholds, or more importantly, how you would refactor that to get into the queue system, just reach out to consulting. We're certainly happy to help you there. And these emails also give us a pretty good starting point, right? It shows immediately what the issue was, and so it gives us a head start in helping that refactorization process. Once you're on the login nodes, you'll probably be first encountering the new user software stack. I'm going to hand it over to my colleague, Brian, to talk a little bit about those activities on Derecho.
All right, thanks, Ben. Hopefully everybody can hear me. If not, I'll get a wave. But yeah, so I guess I've been the primary person working on the module software stack on Derecho. So and I know I've worked with a couple of folks on the test system and also early on Derecho. So I think we've got a decent amount of experience. We're still learning both about the Cray tools that are packaged on the system as well as the SPAC package manager. At least I'm still learning. But I'll give you a little overview. So basically on Cheyenne, we used some internal tooling that we had put together when we launched that machine to install all of the software packages that we build from source and make available in the module tree. So when you run module avail, those are the ones that you see. This process worked pretty well on Cheyenne, but there were definitely downsides. One is that we hand wrote bash install scripts for all of the software packages, which means that there was a maintenance burden there, and B, we may not be importing some of the best practices that other sites have seen because we're just not, we're developing those recipes in-house. And then the other downside is that it really didn't give us a whole lot of functionality in terms of trying to share our build process with the user community. And that's something that we wanted to increase moving forward as well. So on Derecho, what we're doing is we're still trying to maintain a very familiar module tree like you've seen on Cheyenne and Casper, but we're building it on the back end now with the SPAC package manager, which is, it's like, if you're not familiar, it's like Conda or perhaps even like apt-get, but instead of downloading binary builds of a package, it will generally want to build it from source. Now you can tell it to download a binary build as well. And they're moving a lot of stuff in that direction in terms of functionality, but it's originally intended to be sort of an HPC software stack management tool. And this is nice because it also auto-generates all of the LMOD modules, and we can provide templates to it and all of that. So it really automates our process nicely. The other thing that we do here is we put a lot of effort into integrating the Cray modules that they provide, since it's originally a Cray system, including the compiler, the MPI, and also some performance analysis tools and things like that you'll see. Another thing to note about the SPAC stack, the software stack, it should be easy to update. It's publicly visible on a GitHub repo, and it's potentially extensible by users as well. One other thing I'll note on this slide is that Casper will use the same operating system as Derecho. That'll be a SUSE-based operating system. We're moving in that direction in the next couple of months. So you'll see some changes to the software stack on Casper, but it should all provide pretty much the same functionality when we're done. And this will make it so that you can move your workflows back and forth between the systems when appropriate more easily, although the Cray tools won't be on Casper. So speaking of those Cray tools, one thing that we've tried really hard to do is make it simpler to access those. So if you're familiar with using Cray modules on a different Cray system, it's, in my opinion, kind of laborious. So you'll load a programming environment module, and then that'll load all of these other modules that work together in myriad ways to make things work. The problem is if you try to then back out what each of these is individually doing, it's sort of an exercise in wasting a lot of time, in my opinion. And some of these components are really designed to work together. Like the lib fabric, for example, is integral to running the Cray MPitch MPI. So what we've done is we've combined the functionality of a bunch of these modules into their main constituent part. To really simplify what the modules look like on Derecho. So instead of having like 3 modules to determine how the compiler will work, you just load the compiler. And same thing with the MPI, and same thing with the math routines in the libsci module. So hopefully this makes understanding what you have loaded easier, and switching between different compilers and MPIs easier as well. But it is a difference if you've used a different Cray system. One thing that we're trying to do, and I think it's really been beneficial, is have this structure. So we actually have 2 SPAC instances that we see. We have a building and testing instance, and then we have the public instance. And what we'll do is if somebody requests a piece of software, or we just want, we want to build something because we know people need it, we'll build it first in this build instance of SPAC. And then we test it out on the back end, and we do all of that before it ever gets deployed into what's publicly visible module tree. This is a bit, I would say, we did that to a degree on Cheyenne, but I think a lot of times if we wanted to ask or invite the person who requested the software to test it out, we had to then make a public module install. And this occasionally led to instances where like people would ask for something, we'd install it, and then almost immediately they use it in a way we didn't test out. And it's like, oh, it's broken. Well, let's go and let's go back and change that. So now we can actually set it up so that we can provide you a path to load these testing modules, and very easily you can try it out. I've seen this be useful just this week because somebody asked for a Julia install, and we created a test install of it and noticed that there was an issue with the way SPAC was building it. Still need to work out exactly what the resolution there is, but that way we didn't expose it to other folks and be like, okay, well, here's something that has a fundamental problem with it. So it should result in a cleaner software stack and more robust. And also this is all tracked on GitHub. So when there are changes, you can see what's going on behind the scenes. And let's say something worked 2 months ago and it doesn't work anymore, and you suspect maybe it's because some change we made in the software stack, well, you can look on GitHub and see what happened, and also submit an issue to us there. So just to talk a little bit about some known issues and limitations still in the software environment, even though we've put a lot of work into making it robust. So on the MPI side, with the Cray MPitch, that's the only, I'd say, well-tested MPI implementation currently available on Derecho. We do have Intel MPI as well, and we're testing out an open MPI, although that's not public right now. So the Cray MPitch, it's CUDA aware, it's fully GPU capable. It has all the capabilities you would expect. It's the vendor solution, so it supports the Slingshot 11 network that we've talked about, the fabric that we've talked about. And that's really Slingshot 11 is sort of the bottleneck here for getting other MPIs working in a robust way. One thing to note about the Cray MPitch, though, it has some environment variables that need to be set in certain modes to keep it robust. So for example, like if you're running a GPU code, there's this MPitch GPU support enabled, and also an MPitch GPU managed memory support enabled. And if you're running GPU code, you're familiar with what those would do. So it sort of turns GPU support on, and this turns managed memory support on. Don't unset those variables because we go to efforts to set those for you in certain circumstances. So unless you say no that you're not running a GPU code, for example, if you turn some of these off, it can cause nodes to hard crash. We've made this as robust as we can, and it shouldn't be that easy to do anymore. But we saw this a lot on the Gust test system, that with these variables not set and running certain codes, you can cause a node to go down. So that's a bummer. So just leave those alone unless you're very confident that you know what you're doing. MVAPitch 2 is another MPitch MPI. There's support for Slingshot 11 and it's in beta. Once it's been actually released and out of an RC state, then we'll certainly test it. And if it looks promising, we'll deploy it for folks to use. And that should be helpful for container support as well. Intel MPI is installed. It's good for CPU applications. It's of limited use for GPU applications because it's sort of tightly tied into the Intel GPU side of things at the moment. And then OpenMPI is, again, not currently publicly available, but we're testing out a version that may have some fixes for Slingshot 11. So that's looking more promising than it was a couple months ago. There are some compiler issues that we're tracking separately. We have a big spreadsheet of stuff, and we have weekly meetings with HPE to try to figure out how to get the Cray compiler to work better with some of our applications like CISL. So hopefully we'll make some good progress there soon, and we can actually recommend using the Cray compiler, which right now we'll recommend using the Intel, and we'll talk about that more later. And then finally, in terms of the math libraries, there's a bunch of different math packages available, like Cray's libsci, there's Intel's MKL, OpenBLAS is on there. So there's all these different ones. Our recommendation at this point is generally use the math library that is designed for the compiler that you're using. So if you're using like the Cray compiler or GCC, which they provide a packaged version of, then yeah, use Cray libsci. It should work well. If you're using the Intel compiler, probably stick with MKL. And if you're using NVHPC, the NVIDIA compiler suite, they package BLAS and LAPACK routines with that SDK. So it makes sense to use those with the compiler because they're pretty tightly coupled. And then finally, just here's a little sort of cheat sheet. This isn't, fully comprehensive, but hopefully it makes it clear that there aren't too many changes on the module tree. Like when you run module avail on Derecho, it should look fairly familiar. There are some name changes, like GNU is now GCC. Intel is kind of an interesting case because there's now variants of that, and I believe we'll talk more about that later. And there's some other small changes, some of which because the vendor changed, like Forge was bought by Linaro. But yeah, there's some minor changes. Some other more notable changes. A big one is that some software that was available as modules in the past, like Git, is now just in your default environment. And it's a recent version of Git. It's not like the OS version, which could be old and have some features that you see on Stack Exchange that aren't there. And we'll keep that up to date as we move forward. There's probably not a good reason to have multiple versions of Git, although if you do come up with one, let us know. And then some packages will auto-load dependencies. So for example, like if you load the netcdf module, it will auto-load HDF5 since it's a dependency of netcdf4. In the past, we would sort of package these all together into a single module, but now they're split apart. So it's a little more componentized, if that's a word. But that's kind of the way SPAC likes to do it. So we've adopted that, and it should be more familiar if you use other computing systems that use SPAC as well. So I think that's all I'll say about what we've done with the module tree and with SPAC. If anybody has any questions, happy to take them. And if not, I will hand this off to our next consultant presenter, Brett.
We do have one question, at least in the chat.
Yeah.
Does that newer version of Git we've deployed have Git LFS embedded? Do you know off the top of your head?
Yeah, it should. So, I don't know about embedded, but it's in the default compute environment as well. So if a Git LFS command is not working, let us know because it should.
Thank you, Brian. And I want to thank you personally for all the effort you've done to make this very similar to Cheyenne. Hopefully Cheyenne users will feel quite at home. I do want to point out specifically, if we have anyone in the audience who works quite a bit on other Cray EXs, Brian mentioned how the default Cray environment is available, but it's a little bit hidden. So if you have a code that works, kind of out of the box on a Cray EX, such as it is, and you'd rather just interface with the Cray modules, God bless you, but we do support that. Just reach out. We can show you how to do that.
Yeah, and I guess since we're doing thanks, I'll also, and we're at Mesa Lab, I'll thank Jim Edwards for doing a ton of testing of the software stack and also some code development. So shout out to Jim.
Awesome, thank you. Right. Next, I'd like to introduce one of I guess, the newest member of the consulting services team, Brett Newman, who's going to talk to us a little about the file system availability on Derecho.
Thanks, Ben and Brian. I'm
Sorry.
Brett Newman. I'll be going over the Glade file spaces. So kind of start out with what's different, what's the same between the two. I talk a bit about the file spaces themselves, go over how to actually move the data between scratch spaces, and then just talk about some of the timelines. So to start, I won't go over everything in this box here, but I'll just talk about the home space and the workspace. Those are the same. Those don't change for Derecho. So the important thing to note here is that the home space is going to remain backup. The workspace will not. The sizes for those have remained the same. The difference here, the main difference that I'll point out for Derecho and Cheyenne here is that the scratch space is going to change over. Right now, there's two separate spaces for those. I'll cover how to move between those spaces in a little more detail on the next slide. But you'll also just note the changes to the Derecho scratch space. 30 terabytes is the quota as the default. It's going to switch to Lustre, which there's a little more detail on what the implications of that are in the future slides. And then the purge is at 180 days instead of 120 days. Campaign storage, there's some small modifications that'll be happening to that, but unless you're a part of particular collections right now, there's not too much to worry about that. Those are project allocated. So just to navigate through these different spaces within the NCAR environment module, if you load that up via module load, you'll have access to some of these environment variables, so you can just quickly move around and be able to transfer data between them a little bit easier. So one of the things that we want to point out here is that the Cheyenne scratch space is going to be decommissioned. So Cheyenne will end on the end of the year here at 2023. So we want to make sure that you're aware that you'll need to move anything that's important in Scratch over to Derecho. There's a couple different techniques that we recommend for doing that. Smaller files, you can do something simple like a move or a copy. If you have large files you want to move over, there's options like rsync or Globus. I prefer Globus. You've got the GUI. It's a little bit easier to see the status of the data moving across those systems. And then if you do want to move just a complete copy from Cheyenne to Derecho, there's actually a script available, and there's a link at the bottom of this slide that's highlighted. It's back up there. That script will give you an option to be able to sync between Cheyenne and Derecho. So just to go over the timelines here, I want to point out again, Cheyenne, the plan here, the last job will run at the end of the year, December 31st, 2023. So make sure that if you have anything on scratch space that you move that over. As I mentioned briefly, the Glade/P and collection space, that's also going to be retired, but there's going to be modifications to that. That's a bit in flux, so just stay posted on that. It'll likely be moved to the Glade campaign storage space, and we'll work out details on how to transfer any of that data when the time comes. So you can reach out to the consultant services group if you have any questions about moving data, or if you just want to make sure that you've properly moved data over from scratch space. I'll just pause for any questions here.
The only thing I'll mention as well is, as of about a month ago, the campaign storage file system has been entirely accessible from all aspects of Cheyenne. So hopefully that aids in the data migration, because whereas previously you could not access campaign storage from, let's say, a Cheyenne compute node, that limitation has now been overcome.
No, within the workspace, that will remain the same. Yep.
Yeah, the question in the room was, will Glade work be decommissioned? And we will move that behind the scenes for you to a new piece of hardware. So yes, while it currently lives on what we call Glade 2, it will no longer by the end of this year. We will have to schedule a broader outage to do that, probably in the October timeframe. But importantly, no user activity will be required to move work. Thank you, Brett. Next up, we have Negin Sabani. Talk about workflow migration. Now, Natalie, I see your question in the chat now. I believe we'll be addressing this just momentarily. And if not, we'll pick it up after the fact, after Negin's discussion.
Hello, everyone. My name is Negin Sobani. So in this section, we're going to talk about the workflow migration. Specifically, we're going to talk about the compiling software, how it's different from Cheyenne, and then job monitoring, job executions, and then job submissions, and then finally we'll talk about the Scratch Lustre file system. So first thing first, compiling software and compiling code on Derecho. So the Derecho users have access to different compilers, many different compilers. Via the module utility, they have access to Intel Classic and OneMPI. They have access to Cray compilers. They have access to NVHPC compilers and GNU compilers. So similar to Cheyenne and Yellowstone and previous machines, wrapper scripts are loaded by default via the NCAR compilers module to streamline the compiling and linking process. Basically, it adds and include it adds the include header and library path flags for you, so the compiling code would be easier. One big difference from Cheyenne and previous machine is that the wrapper script no longer explicitly add library references, so it doesn't add the LNet CDF or -LNet CDFF for Fortran. Basically, so if you are seeing if you have a code that compiles Bell on Cheyenne and it doesn't compile on Derecho, complaining about like missing a library, like missing netcdf, for example, it's probably missing the -LNet CDF and -LNet CDFF for Fortran codes. So this is something to keep in mind. I'll talk more about each one of these compilers next. So this is just basically a cheat sheet of all the compilers that are available on Derecho, and each compiler suite has support for Fortran, C, C++, and the commands, the native compiler commands that's used for each one of these compilers, and the commands for MPI, for compiling with MPI programs. When NCAR compilers are loaded, and the flag to enable the OpenMP and compiling with OpenMP. So first, and the compilers is like loaded by default on Derecho is Intel compilers. So similar to the previous NCAR system, the Intel compiler suite is available via the Intel compiler modules. It includes compilers for Fortran C and C++. There is a change basically here from Cheyenne, and it's basically like an Intel. Since 2020, Intel is basically like moving more towards the client-based Intel One API, and it's like basically retiring all the Intel classic compilers. So i4, ICC, and ICPC that a lot of us used to work with will be all replaced with the new Intel One API compilers, the IFX, ICX, and ICPX in future. And right now we have a permutations available, different permutations, 3 different permutations of these compilers available on Derecho. So we have the Intel module, we have the Intel Classic module, which only has the classic compiler, Intel Classic compilers, i4, ICC, and ICPC. We have the Intel One API, which only has the One API compilers, and we have the Intel module, which has a hybrid of both the classic and one API compilers, and we can talk about it more. Intel compilers provide several different optimization and vectorization options, and you can all refer to the manual page for exploring different optimization flags that are available on Intel compilers using the man and the name of the compiler of choice, or using the --help for a shorter version of it. But something to keep in mind is that some of the flags that are very commonly used, and we encourage users to use them on Cheyenne, no longer work on Derecho because of the difference in the architecture of the systems. And the 4 that's like most the users should avoid at all costs on Derecho is like the -X host, -AX host, the X-core AVX2, and the AX core AVX2 flags should be avoided. And Derecho users are encouraged to use the MARC core AVX2 flag for better optimization. But this flag, just to be aware, when Cray programming environment is loaded in the system, and I'll talk about that in a few slides, it will automatically add this this better optimization flag for you. So that's that. Next, users have access to Cray compilers via the CCE module. So this shouldn't be mistaken with the Cray programming environment. So I know the naming are very confusing. But yeah, so the Cray compilers are available via the CCE module, and the Cray compiler corrections provide Cray Fortran, Cray C, and Cray C++ compilers using the CC, uppercase CC, and FDN commands. They're a little bit oddly named, like capital or uppercase CC is like for C++, lowercase is for C. This is mostly for those who are familiar with Cray compilers on other systems. They might know that Cray compilers and Cray compiling suite basically does not provide MPI wrappers similar to the other compiler suites. So it doesn't provide the MPI CC, MPI CX, and MPI F90. But basically the FDN, CC, and CC, like the uppercase CC or capital CC will include all the basically links for the MPI libraries. But when you have for basically ease of use and of the users, when they have the NCAR compilers module loaded, the module basically automatically translate the MPI CC or MPI CXX to CC or capital letter CC for the users. Basically, it's as a convenience. So if you've worked like with other Cray compiler, like Cray environments before, this might seem odd to you, but basically this will make sure that it's like continuous for users across different compilers. And another thing is that Cray compilers enable offloading of computations from CPU to GPUs via OpenMP and OpenACC. Speaking about GPUs, GPU applications should be built on Derecho, either with the Cray compilers or with the NVIDIA NVHPC compilers. And to access to NVHPC compilers, the users have to load the NVIDIA HPC SDK, which is Software Development Kit module. So NVIDIA HPC SDK is a comprehensive suite of tools, compilers. It has like performance analysis tools and applications such as Nsight. It has support for CUDA, OpenACC, OpenMP. And it provides the access to NVHPC compilers, which is NV Fortran, NVC, and NVC++. So the compilation flags for GPU codes using the NVHPC compilers depend on the GPU programming paradigm that the user chooses. So if they want to use OpenACC, it will be different. If they want to use OpenMP, it will be different. And I'll talk about them in the next slide. And another thing is that always, again, like this would be something that I mentioned earlier, but it's always a good idea to refer to the manual page and read the manual page. I know it's long, but there are a lot of useful information in the manual page about like optimizing and good examples as well. So this is one example of compiling GPU codes with OpenACC and with the NVHPC compilers. So basically, the user need to add the -ACC flag for that. So here, the user added that -ACC flag, and that will basically compile the code with OpenACC directives. There are other options that are available. So for example, the -m info is equal to axle flag give you some more information about the GPU acceleration decisions that the compiler made. There are other actually flavors of this flag that's available. So if you do like -m info is equal to opt or -m info is equal to all, the opt one will give you, for example, the optimization decisions that the compiler made, and the all one gives you all the decisions. So it just refer to the manual for the compiler. It will give you a lot of good examples. This is usually a good flag to basically enable if you want to dig deep into the performance of your code. You can also target specific GPU architecture with the GPU, the -GPU flag, if you want, for example, to compile it for different GPU architectures. With OpenMP, it's very similar to OpenACC. So you can compile with GPU offloading and adding the -MP is equal to GPU flag. And the diagnostic, the target flags, everything else is very similar to the OpenACC. So I'm not going to go through that again. And then compiling code with CUDA. So I had like two examples here. One is a simple Fortran code that has CUDA. So basically for that, you can directly use the MV Fortran with the -m CUDA flag to basically compile that code. The second one is a more complex code. It's like a mix of C++ and CUDA code, which require a two-stage compilation basically process. First one is like compiling and building the object file using the MVCC, the NVIDIA CUDA compiler. And then the second step would be linking the CUDA objects that you create in the first step using the non-NVIDIA HPC compiler. For example, here is the G++. And now I'll talk about the Cray programming environment. So this is the Cray program, the Cray PE module. So this should not be confused with the Cray compilers. So the Cray programming environment basically is it's a suite of HPC-oriented software that's the HPE provides basically to make development and optimization on Cray basically architectures easier. And when you load Cray PE module, which is loaded by default, it contains drivers such as CC and then capital letter CC and FDN to compile code for other compilers. So these are basically just wrapper codes for that points to other compilers. And specifically, I included examples here. So here, the user had for example, the Intel compiler loaded, and then again use FDN, CC, and capital letter CC, but these are pointing to the Intel compilers, not the Cray compiler. So this is basically just a wrapper around the compiler that's loaded. And here is basically an example that shows it completely. So for example, here the user has the Intel compiler loaded, and if they do FDN -- version, they can see that it's basically pointing to i4 compiler, which is the same as the Intel compiler. So that's what we expect. So if we change it to NVHPC and do the same FDN -- version, it's now pointing to the NVIDIA compiler. And one of the questions in the audience in the Zoom was actually like, because in the other supercomputer that uses like Cray programming environment, it's mostly actually advised to use the FDN CC and the capital letter CC. But actually at NCAR, for the user convenience, both of them, you can use either like FDN, which is a wrapper around it with like some optimization added, or you can also use the i4. So it doesn't matter which one you choose. Both of them basically will be the same thing. And it includes the optimization as long as the Cray PE module is loaded, the Cray programming environment is loaded. And then another thing that's might be of interest to a lot of our users is that the recency compilers that are based on Clang, for example, the new Intel One API or the Cray and the Cray compiling environment, and the Cray compilers, they are basically enforcing some C standard compliances checks. So some of the compliance checks previously, they just gave like warnings, and now users might see errors that are happening when the code is not compliant with the C standard. And the best way around it is actually making sure that your code is compliant with the specified standard. And you can always contact us for additional help regarding this. But if you want to like some really quick fix around it, you can also you can basically force the compiler to ignore these warnings or errors using the -w no error is equal to. For example, this one, the compiler complained about the implicit function declaration, and adding this -w no error is equal to implicit function declaration basically force the compiler to ignore these errors. And there are other flavors of this error, and the same, the -w no error is equal to whatever the compiler complained about will resolve it. And then finally, there are basically 3 new environment variables that are added that basically provides some cross-compiler and cross-system development strategies, basically. So this is all part of the new spec user software environment that Brian put together. So the 3 new environments are the NCAR build and compiler, NCAR build and MPI, and then NCAR build env. And then you can see these are all dynamically changing based on the compilers, based on the modules that are loaded. So for example, here, the Cray MPitch is loaded. You can see these environments are pointing to Cray MPitch, and then the user, sorry, this one, GCC was loaded with Cray MPitch. This is also pointing to GCC with Cray MPitch. And when we have NVHPC with Cray MPitch, these environments are basically pointing to that as well. Basically, this will make it easier to manage the environments and manage the modules that are loaded for a lot of users. And with that, I'll hand it to Rory if there are no questions to talk about running jobs on Derecho.
Thank you, Megan. Believe, let's see, Natalie, I think we addressed your question. Let us know if otherwise. Brian has a question, perhaps.
I'll just turn on, just back on. Yeah, I just wanted to clarify for Natalie, you know, what Megan said is absolutely right. But so it's really the interaction of the 2 different compiler wrappers that we have on the system. So there's the Cray wrapper, which is the CC, CAPCC, and FTN. And then there's our NCAR compilers wrapper, which does some additional translations. So it is equivalent to use CC and say ICC or CC and GCC if you have both of those wrappers loaded in your module environment. So that's like the Cray PE module and the NCAR compilers module. If you start stripping some of those wrappers away, then the behavior changes. So I just wanted that to be clear. If you say run ICC and then run CC and you see a difference, then it's probably because you've changed your module environment from the default. And you know, we can always take questions and tickets, but it can be a source of confusion. So I just wanted to emphasize that point.
Thank you. So when many of you RSVP'd, there was a section to ask questions. One of the questions we got ahead of time is, do we need to recompile on Derecho? And probably the answer is now obvious, but yes. To get optimal performance or even any performance moving from Cheyenne, you're going to need to recompile. And you're probably going to want to port your PBS scripts as well. Certainly asking for more than 36 cores would be a good idea. So next up, Rory Kelly's going to tell us about the details associated with running jobs on Derecho on both CPU and GPU nodes.
All right, so yeah, as Ben says, I'm going to talk a little about running jobs. I'm glad we all know how to compile things now, thanks to Megan. But yeah, what happens if you actually want to run something after you've compiled it? That's what we're here for. So the good news is if you've run anything on any NCAR system for the last decade, it's largely going to feel the same. PBS is still the Q system, so the commands qsub, qdel, qstat, all that stuff still exists. No major changes in sort of like that low-level user interface. You know, we've documented all this stuff for years. I'm not going to do a deep dive into PBS commands. Just know your general interaction with the Q system is the same. So one difference is just the queue name, a little different. So it's just called main is the most probable queue you'll submit to. As John mentioned this morning, there is like a development queue and a preemptible queue, but the vast majority of your work on Derecho will get submitted to the main queue. And then selecting between CPU node types, GPU node types, or a mix of node types, all those are possible, but you do that via a PBS select statement. So resource requests don't need to go to a different queue or anything. They'll be routed to the right spot by PBS so long as you include a select statement. I have examples later in slides that show some of these select statements, so you get to see what that looks like. It's important to bind MPI ranks and OpenMP threads to get good performance. We'll go into a little bit about how you do that and why you need to do that. And then the assignment between MPI ranks and GPUs needs to be done in some way. One way to do this is setting CUDA visible devices. We have some scripts that do that for you. You can also set it yourself. You can also do these types of things programmatically inside of CUDA code. And then it can be important to place MPI ranks near the NICs that are going to be communicating. There are multiple NICs on a GPU node, and so having a GPU assigned close to a rank can be helpful in certain cases where GPU codes are doing a lot of MPI. So again, that's pretty easy to do. It's accomplished by an environment variable. I'll have an example of that later. But just knowing that binding is important generally, like it's something you should think about when you're running your codes on Derecho. And this is a little bit of a schematic why it's a big mess. And the reason this picture is a big mess is because, processors are a big mess these days, unfortunately. So this is just showing all the cores that exist on a CPU node in Derecho. And what the diagram is trying to get at really is that there are cores and there's memory. There's multiple levels of memory within the memory hierarchy. And some of the memory is close to the core that a CPU, your code is running on, and some of the memory is really far away. And so what you're trying to accomplish is the CPU that is allocating memory, you want that memory to be allocated as close to the place it's going to be used as possible. And you accomplish that by binding your MPI ranks. And binding just means, more than anything, not allowing the operating system to shuffle things around at runtime. So you say, put this MPI rank exactly on this CPU, on this core, and then when memory allocations occur, they occur on the memory local to that core. The memory doesn't move around, the CPU doesn't move around. And so you get good performance. So yeah, something to think about for sure. Don't try to just run without thinking about how your memory is allocated in relation to where your processes are. Okay, so I just gave you a big long talk about why it's important. One thing I just want to draw your attention to quickly is oversubscribing resources kind of doesn't play nicely with the MPI, the way Cray impitch binds things. It can do some pretty funky binding. So just be aware of that. There are ways to, I'm not going to go into like an oversubscription, like a good way to bind ranks if you're oversubscribed. Oversubscribed, by the way, just means like, so you have 128 CPUs on a node. If you want to run 256 MPI ranks, a thing like that's possible, but the default binding tools I'm about to talk about might not work in that scenario. So if you have a need to do that, contact us is what I'd say right now. So quickly, for a non-oversubscribed way you would do this, this is all these commands, by the way, are via Cray impitch at the moment. As Brian mentioned, that's kind of our primary supported MPI at this point. So all these examples are Cray impitch. But so the way you do, the way you would launch, for instance, like a 2-node fully subscribed, so 128 MPI ranks per node task would be to say, okay, MPI exec-n256, so I want 256 ranks, and then ppn 128, I want 128 of them on each node, and then you're executable. By default, if you don't tell MPI to do any binding, it will do binding for you, and it's going to bind to a thread, and a thread in this context means, what's a good way to describe it? So there's 128 physical processor cores on the system. The operating system thinks there are 256 because the cores they have multiple hardware threads. So a thread is like a single thread context in terms of the CPU. It's sort of like there are 2 threads for each physical core. So by default, MPI will bind your task to a single thread, which means it won't allow it to switch thread context within the CPU. It might be advantageous every once in a while to bind to a core instead. So you can do that by this next line down I'm showing. You tell it -- CPU bind core, and then it binds it to a core, meaning it can actually, your MPI rank could float between multiple threads. So it could wander back and forth between the 2 threads, but all the memory hierarchy of those 2 threads should be the same. Everything will still be local. So, and particularly like I mentioned before, in an oversubscribed scenario, that could be useful to bind to a core instead of a thread. But if you need to do that, let us know. Another thing, so if you are doing OpenMP, it's also important to bind, when you're binding with a mix of MPI and OpenMP, then you need to bind MPI ranks and optionally bind the OpenMP ranks additionally. By default, the way you want to bind the MPI ranks now is, so you don't, what you're trying to accomplish here when you have like, for instance, in this example, I'm showing 32 MPI ranks on a node and 4 threads per rank. So we're still using all 128 cores. What you're trying to accomplish with the binding here is making sure you don't bind the 32 MPI ranks on the first 32 CPUs, because you still want to spread them across the 2 sockets and across the numeric domains on chip. So this method of binding will just spread them out. That's what's happening in this line. And so you would accomplish that by saying MPI exec CPU bind depth. Depth is sort of like the number of threads. So I would say bind according to the depth, and then dash N64 would be 64 ranks, and dash PPN32 would be 32 per node. And then a dash D4 is saying depth is 4, which is equivalent to saying OMP num threads is equal to 4. And then in that binding scenario, now it's spread out your MPI ranks, but your OpenMP threads could still wander around within the cores that the MPI rank is bound to. So there are many different ways to bind OpenMP ranks. The ones I'm showing below are sort of the OpenMP standard way. There's also, each compiler has its own special environment variables to accomplish this, like Intel has KMP threads and so on and so forth. But I'm just showing the OpenMP defined standard ones. So this is probably a good way to try binding OpenMP by default for your application, is to say OMP places equals threads. Again, that's the same meaning of the word thread that I mentioned before. And then OMP proc bind equals close just means like put all the threads bound to a given MPI rank, sort of stack them together closely. There are many options for that. You can read man pages or Google OpenMP standards if you want to see some of the other options. But setting those in a hybrid application is generally a good idea also for performance. Okay, so now I'll get into a couple of quick examples. All the PBS stuff up here, like I said, I mean, it's very, very similar to what you've seen on Cheyenne. So I won't go into it in great depth. I'll probably mostly just focus on the select lines here, because one annoyance of the current runtime environment for the queue system on Derecho is that you have to sort of double specify a lot of things. You have to tell PBS you want a certain amount of resources. So like in the select line here, I'm selecting 2 nodes, 128 CPUs on each of those nodes, and 128 MPI processors on each of those nodes. And then when it comes time to launch the application, you have to sort of do the math for it, which is unfortunate. So you have to say, I want a total of 256 ranks. That's the 2 times 128. And then I want 128 of them on each node. So you're going to end up double specifying a lot of information, which is a little error prone. We have some scripts actually that simplify this, and we'll probably unleash them in fairly short order. I'm sort of waiting for OpenMPI to be available on the system too, so we can kind of cover all bases. But yeah, just know for the moment under Cray and Pitch, you have to double specify and double check your math, because that's one place we've seen a lot of people make simple mistakes in batch scripts. This is the same example basically with a hybrid MPI and OpenMP job. So same thing, still selecting 2 nodes and 128 CPUs on each, but now 32 ranks and 4 threads. And then, as I mentioned before, these binding variables are a good default for OpenMP, I'd say. And then the way you bind, as I mentioned before, double specifying all the math again, binding according to depth, asking for 64 total ranks. Now that's 2 times the 32 ranks and 4 threads on each. So, as I mentioned too about trying to get a GPU assigned closely to the NIC that it's going to be communicating over for GPU MPI codes, that's done by setting this impitch OFI NIC policy equals GPU. I wouldn't say, my experience isn't like a super critical. This is not going to be like a factor of 2 performance difference. It seems like a small performance difference, but I have seen it never be harmful and sometimes be sort of helpful. So I would generally recommend trying it if you have a GPU MPI application. Like I mentioned, the MPI rank, the GPU device ID, you can do it programmatically. You can set CUDA visible devices yourself. We also have a helper script that does it called set GPU rank. And set GPU rank is in the in-car env module. So most likely you have that loaded by default in your path. And it just sets this CUDA and visible devices to be unique for each MPI rank. So they're landing on different GPUs. So the way you would use that script, if you are running, you want to have our CUDA visible devices set method, then you would do MPI exec, your same arguments, your dash n's and your dash ppn's, and then you do the set GPU rank before your executable name, and that will just set that environment variable for you. Okay, so here's another batch script example, again, just focusing on the select line and the MPI exec line. to run a GPU code here. The only difference really is that now the GPU nodes only have 64 in CPUs, so make sure you're specifying 64 in CPUs instead of 128. And then like in this case, I'm doing 1 MPI rank for each GPU, so I'm saying give me 4 MPI ranks, give me 4 GPUs, and then in the launch line, now I'm having to say 8 total ranks, 4 on a node. I'm using that helper set GPU script. Another common case here is, oh, I wanted to back up. I added a slide, but I think because we're in presentation mode, it's only updated on the slides, but not in the presentation. As John mentioned this morning, we do also have the ability through PBS to enable MPS mode, which is NVIDIA's multi-process server. And what that means is if you launch multiple MPI ranks, so like 8 MPI ranks on 4 GPUs, that'll work in this scenario right now, but what happens is your MPI, if you have 2 MPI ranks sharing a GPU, they won't execute simultaneously, they'll kind of time slice. So it's probably more efficient to have them run simultaneously, and you do that by enabling MPS. And so to do that, you would just add a colon MPS equals 1 to the end of that line. Oh, that feels so dangerous. Are you sure? Okay.
No.
Like this.
The first escape got.
This has all been terrifying. Nope. Okay. But I think if you're looking at the slides online, that new slide probably exists, and if not, the next time we show this presentation, it'll exist. But anyway, yeah, adding an MPS equals 1 will enable oh yeah, it is there now. Cool, good job, Ben. So yeah, adding that MPS equals 1 turns MPS on, and now you can have multiple MPI ranks assigned to a single GPU, and as long as the kernels will all fit at the same time, those will execute at the same time instead of being time sliced. Another case that's common is sort of like using other Python-based frameworks to do GPU code here. The only thing I'm really trying to show here is you're selecting the number of resources. You're still saying I want however many nodes with however many GPUs. You don't necessarily need to specify MPI at this point, because most likely, like if you're doing PyTorch or TensorFlow or something, then the distribution of work over GPUs is going to be handled by the framework itself and not MPI. So you can leave the MPI ranks off. And then also the binding is done also internal to the framework typically. So the launch line for that select statement is a little simpler. You would just do something like Python and then the name of your Python code, and hopefully the framework itself is intelligent enough to spread the work well over the GPUs. Other environment variables that are useful for MPI, I will say I think there's a lot of useful detail in the Cray MPitch man pages. So actually doing man MPI and man MPI exec can give you a lot of info. There are some settings that might not mean much to you, but if you're having trouble, they can mean a lot to us in terms of helping you debug your code. So ways to collect some additional statistics and information and debug output from MPI are some of these environment variables I show below. The MPitch OF5 verbose, like it says, just gives you a lot of output. And then similarly with the NIC verbose, these are just kind of giving you counters and information on what the MPI library is trying to do, where it's trying to communicate, and where things might be going wrong. Some additional counters can be collected with this OFI CXI counter report. The levels here that I've bolded are the ones that I find to be the most useful level, like the best compromise between information and information overload. So like in this case, 3 seems to be a nice compromise. And then similarly, MPitch memory report, I think is pretty useful, probably for, not just for us, probably for general people using MPI too. Will give you some information about how memory was used by the MPI library. So those are things I recommend turning on, particularly if you have problems that can help us looking at your debug output. And I think now I'm turning it over presumably to Ben to talk about.
I think that's right. What's the next slide look like?
Yeah, well, we don't have a transition slide.
There we go. Perfect.
Hello?
Is there a question?
Not sure. I'm not seeing one in the chat.
Okay.
Thank you, Rory. One thing, so Rory has led the application workflow test suite, which was executed on Derecho first during the acceptance phase, and gave us kind of the contractual obligated benchmark numbers that we talked about earlier in the performance. One thing I do want to mention though, is one of the things that we've seen on Derecho, especially coming over from Cheyenne, is a larger performance sensitivity to these hybrid parallel approaches. So if you have a code that has both like MPI and OpenMP level parallelism, definitely encourage you to do some parametric studies at the outset, because whereas the Cheyenne compute nodes have 36 cores in a given node, Derecho is 128, at least on the CPU nodes. And so the relative balance between CPUs and network has changed a little bit. And so we have seen, I'd say maybe more performance variability or more performance benefit from hybrid parallelism in some cases than we did on Cheyenne.
I think you could, since you're talking about it, you could mention like on Cheyenne, the sweet spot, if you had to pick one, would be like 2 threads per rank. On Derecho, the sweet spot's 4 threads per rank.
Yeah, for sure. So especially if you've run hybrid MPI, OpenMP, and you've kind of settled on 2 threads per rank from Cheyenne, you may very well double that, or even, again, do those parametrics. But 4 threads per rank has been a pretty good sweet spot there. And just from a technical perspective, yeah, it turns out that we have twice as much network bandwidth per node on Cheyenne, but we have almost 4 times as many cores. So that, if you're actually looking at a single MPI rank per core, there's less bandwidth there than there is on a Cheyenne node. Okay, let's see, we've got 28 minutes left. I'm going to talk a little bit about the Luster Scratch file system on Derecho, and also some of the MPI IO options available to interface with it. If we have time, may I please show the hybrid slide one more time? I certainly can. We got a couple of those. Let's go back to, I'm believing this is the one we're talking about. So we had a question online, if we could please show the hybrid slide one more time. I'll pause here in case there's any specific questions related to it. There's another question in the chat. Do you have to reload necessarily module environments in the PBS script? It doesn't inherit environment modules during compile. So certainly it's not going to, if you load a non-standard set for compilation, you will not get that inside your PBS batch script. You will get the default environment, whatever that happens to be. And so because I make that point specifically, as you go through time, we may have reason to change what the default environment is in the module set. We will communicate that as we typically do, but you could be surprised, right? So a best practice for reproducible scripts, you want to come back in 2 years' time and launch the same PBS script. It can be beneficial to specify specifically which modules you want, and even occasionally the exact versions of which. So
I would say I only omitted the version numbers on that slide.
Yeah. Yeah, so here's a good example of the actual version numbers included, so that you could come back in 2 years' time when CUDA is up to version 12.2 or whatever. We do have a question in the room as well. John, sure. I'll repeat it if it's a good question.
It might not be a good question. So this is an example for single node. If I'm doing a multi-node, multi-GPU, would I use MPI EXEC to carry that out rather than so if I was on like a Slurm, like it used to be, I could use srun to do that. But I've not really played around with multi-GPU, multi-node stuff like on Casper. So now that we're on Derecho, we're going to need that. Exactly, either or, yeah.
No, I think as far as I have seen, I haven't done it with TensorFlow. I don't know, you probably do. Of course, no, as long as you ask for the nodes.
Okay, that's great. Cool.
Yeah, so the question was multi-node PyTorch. Does that need to be launched under MPI with MPI exec? And it sounds like the answer is no, which means the internode communication's done not using MPI, right? So when you're running under PBS, and you can test this interactively as well, just get an interactive PBS session. The scheduler defines an environment variable PBS _ node file. I was gonna say, thank you. And so that's a file that's dynamically created for every single job. It contains one entry per host, per rank effectively. So in general, you would expect to see like 64. Well, for this example, you would see probably 64 entries of the same host. And so that gives you everything you need. Sometimes you want to pipe that through like sort or unique if your framework is only expecting one line per host as opposed to repeated. But we use that a lot behind the scenes for different things. If you have any issues with that, feel free to ask, reach out. Okay, let's see. I can no longer see the questions, so somebody keep me honest with the chat, please. All right, so Lustre is the default Scratch file system on Derecho. As Brett told us, it's mounted under Glade Derecho Scratch. That is the preferred location for large data, both input and output. I want to go into a little bit of detail on how Lustre achieves its parallel performance, because unfortunately, sometimes it's a little bit more visible to the user in terms of very high performance or low performance if it's not being used optimally. And I'd say this is in comparison to the GPFS file systems that most Cheyenne users would be used to. So the way that Lustre achieves high performance is through striping files over many storage servers, and we'll talk about that schematically here in just a second. We do attempt to provide sensible defaults applied system-wide, but there may be examples in which you want to stray from that default, or we encourage you to stray from that default as part of a performance investigation. And so all the interface to all the striping is through the LFS command. The LFS command, Lustre file system command, has a number of sub options, but the two most important in this regard are LFS get stripe or set stripe. There's another additional tools provided under LFS that can be beneficial. Probably the one I really want to point out is if you often use the Linux utility find and you're working on a Lustre file system, definitely check out the LFS find replacement. It's very, very similar. In fact, most of the command line arguments are identical, but the important aspect is it traverses the file system using knowledge of the data structures used internally in the servers. And so it's kind of the least impactful way to walk a 60 petabyte file system if there is such a thing. LFS df-h is a good one. If you think that the file system's having any kind of issues or Scratch isn't behaving on you, run that command real quick. You should see about 100 lines of output. And if you don't, it means it's probably hung at a server that's down. We've had pretty good stability so far, so hopefully that's not an issue you need to worry about too much. The last thing I want to touch on in this little section is that Cray impitch, as we mentioned several times, is our preferred and default. Supports MPI-IO. It uses the Romeo implementation, and it has some additional tuning parameters that are both common to Romeo, but also Cray specific that are relevant to Lustre that we'll talk about here in a second. So from a concept overview, Lustre striping is very simple. You take a file shown schematically here at the left, file A, and it's broken into chunks indicated by these green blocks. And the first 4 chunks are identical size here. That is a stripe width. The last chunk is intentionally shown to be a little bit smaller because it's not necessarily evenly divisible. Those stripes are going to be spread across one or more storage targets. Shown here, these are just individual hard drives, 0 through 3. In our case, each of these storage targets is a pretty substantial drive array. So each one is about half a petabyte in its own regard. But regardless, that's the fundamental mechanism that files are stored. So by striping at fixed widths over a large number of devices, you can achieve write rates which are dramatically higher than any single device could support. The historical challenge of Lustre, though, is then finding a one-size-fits-all striping pattern for general purpose file systems. That was a huge issue, I'd say, in the first decade plus of Lustre deployments. A little bit more recently, there's been a new technology introduced that we're employing called progressive file layouts that mitigates most of this concern, but not all of it. I'll talk about what a PFL looks like and its intent here. So what a PFL does is takes that concept and then applies it at one more level of abstraction. So in this case, rather than having a single striping template, I'd say, there's you can have an arbitrary number. This schematic shows 3. We actually employ 4. I'll show you here in a second. But the idea is for small files, you don't necessarily want to jump immediately to striping over a large amount of servers. If I have a megabyte file and I say, oh, there's 24 servers, I want to use them all, I'm actually probably going to have a performance detriment. There's just not enough bandwidth to keep that pipe full. And so a PFL allows you to do this progressively through a file. In this case, if we have this blue stripe pattern, which applies to the first 2 megabytes of this file in our example, only stripes over 2 servers. That way we're not incurring additional network overhead where it's not yet warranted. As the file grows, in this example, beyond that 2 megabyte boundary, we encounter another striping pattern, in this case, 4 stripes, and so on and so forth. And so the general approach is what I just described. It allows us to have small stripe counts for small files or the small portion of the beginning of a file, and then grow that as the file gets larger. So the way that this is all governed is through the LFS set stripe command. Let me say at the outset, so these properties are inherited on a directory by directory basis. So before any user accounts were created, we set a default stripe configuration on the entire file system. And that might be fine for you. You could go your entire career on Derecho and never worry about this again, and that would be great. But probably won't be the case for everybody. So that's what we're talking about right now. The way that we've decided to lay out this PFL is the first, for a file that's 16 megabytes or less, we're actually going to apply a single stripe count of 1. And so that's intentional. It is not until you really get above a 16 megabyte boundary that it would even be worth the overhead of incurring additional storage servers in general. So that's our approach here. So for 16 megs to 16 gigs, you'll then be exercising 4 stripe counts, above 16 gigs, 12. And then finally at 64 gigabytes or larger, by our default pattern, you are striping over 24 of these targets. 24 is actually the number of storage servers we have. So at that point, you are interfacing with basically every network card that we have in a storage server. So you have the opportunity to exercise all of the file system network bandwidth at that point. Infrequently, occasionally, you may want to go above 24, but that would be as a result of a tuned application that's doing MPI-IO, and you do some parameterization to figure out where your sweet spot is. The general considerations here are that for large or aggregated files, so think 1,000 ranks all writing to a single file using MPI-IO or netcdf parallel files, the default striping should be adequate. If anything, you may want to experiment with growing your stripe count faster. But we've seen decent performance in general with this configuration across the board. The other extreme is if you're doing per rank file IO. So say you've got maybe a wharf run where every rank is outputting, maybe a gigabyte file or even larger. Our default will have you striping over 4 servers or more. You may want to ratchet that in, because if every rank is striping to 4 servers, then basically you're doing 4. That's a whole lot of what are called RPCs. In the Lustre speak, it's a lot of network traffic that's going on behind the scenes, maybe more than is helpful. So that's probably the most immediate example where you may want to back off from the stripe count that we have here. And then lastly, as I mentioned, striping is inherited from a parent directory, or you can set it on files directly at creation through some environment variables we'll talk about here in a second. So finally, if you're working with a code that uses MPI-IO, definitely encourage you to do some performance tuning ahead of time to figure out where the sweet spot is. We've done a fair bit of this with the CSM developers already, but there's certainly other codes out there that probably have unique use cases. As mentioned a few times, man MPI has a full listing of these environment variables, but 4 of which we found pretty useful are, first off, mpitch MPI-IO hints allows you to pass literally hints down to the IO subsystem that's can be quite granular. In this example here, I'm saying for any file that you create through MPI-IO, I want you to apply a striping factor of stripe count, and that should be an integer, striping unit of stripe width, which is also an integer in bytes. And what that will do, if set, will basically override any of the default progressive file layouts or even other manually specified stripe patterns when creating a file. So if you say 90% of your file IO has one particular optimal pattern, but that other 10 needs some additional treatment, you can specify not just the star in the first example here, you could specify a file name glob, for example, that lets you get quite granular in how this gets applied. The next couple are really important to know what's happening behind the scenes as you do this tuning. So the first one, in pitch MPIO hints display, just regurgitates all the hints that are applied, both the ones you specify and also the default. So it gives you a good point of departure there. And then the timers and stats aggregate things to let you know what your actual IO performance is. I will say there's a lot of knobs in there, which is why we don't have general guidance for every application. So have a look and experiment and let us know what you find. One note of caution, striping patterns defined in this way are only applied when you create a file. In particular, if you're overwriting a file, they have no effect. Whatever existed already is what you get. So that's especially important if you're doing parametric studies. Remove files in between so you don't accidentally get a misleading result. This is an example of what some of those outputs create. This is an LES code, in this case run on nearly 7,700 ranks on a total of 240 nodes. Using those, the stats display, you can get output as follows. What you can see in the bottom two lines is it nicely summarizes the raw write rate is actually what's being achieved when MPIO is hammering the disk subsystem. So in this case, we're about 160 gigabytes a second, a little less than half of the system's overall performance, but that was achieved by writing from 240 nodes, so less than a tenth of Derecho's compute capability on the CPU side. And the net write is inclusive of any MPI traffic required to relocate the data prior to putting it on disk. So these last two numbers are kind of what you're looking at as you're trying to optimize write and read rates by tuning any of these MPIO parameters. Let's see. All right. I think what I'd like to do before we break for lunch. So Mia Trahan is another new consultant who joined us last summer. She's going to run through some of the additional resources that we have for getting support on the system. This includes the ticket system, but also some novel capabilities here.
Okay, so the question is, all the examples seem to call MPI exec, but is MPI exec MPT still available on Derecho? Nope. Yeah, so we moved off of that. Our vendor has completely changed our MPI, so this is going to be a little bit different. So you'll need to shift over from that MPT command to just standard MPI exec. Okay.
Yes, thank you very much for that. MPI exec MPT only existed in the HP MPT option on Cheyenne, which does not carry over. All right, so just a real quick check on what we're going to do for the rest of the afternoon. Mia is going to run through some of the additional resources that we have for getting support on this system, in addition to the familiar trouble ticket system. We will then break and rejoin at 1 p.m. for sort of a more office hours open discussion question. We do have a list of questions that were submitted with your RSVPs, as I alluded to earlier. We don't know who asked what, which is fine. And we also don't know which of those topics are specifically of interest this afternoon. So as we break at the top of the hour, if there's anything that people are looking for more clarity on the afternoon session, feel free to drop it into the chat and we will then focus on that as we come back. All right.
Thank you, Ben. Yeah, so I will just go ahead and pass us along a few extra resources so you can just take a look. Right here, we have this spreadsheet, right, that just generally goes over the differences between moving from Cheyenne to Derecho. and with links to docs if you need to take a look at them. But just a quick overview, right? So we actually have GPUs in the login nodes now, right? It's similar, right? Where we only have 6 CPU nodes or 6 CPUs per node, right? And now we have 2 additional GPUs on there. Next, of course, we have more cores. Yeah, we have about twice as many. We have different interconnect. I'm not gonna go through all this, right? So you can take a look at anything else that you want to like hop in here. But yeah, as you can see, things have changed. Please make sure to do your adaptions based off that. All right, so getting help. So this is like really important. The documentation page, right? It's really, really helpful. If you don't know where this is at, please take a look at it. It's just at arc.ucar.edu/knowledge-based documentation. Okay. Super important, right? It'll answer like most of the things that we talked about today, as well as like any other kind of major questions you might have. Next, a big help is of course the consultants here at CISL. CISL Help Desk. I'm sure many of you have interacted with it before, but please feel free to submit us a ticket. We love answering questions. It's generally like our best way of communication. Next, I want to point out something super cool. We also have virtual consulting through appointment now. So now you can actually request, and I'm going to go ahead and click this, which is super dangerous. I'm sorry if I break it. But if you take a look in our documentation page, we actually have like a list of consultants, right? And you can go ahead and pick to see like whoever you want to go ahead and list a kind of appointment with, right? And let's just say I want to meet with Ben. You can go ahead and select that, right? And you can specify a specific time. And then you can go ahead and click that, and that'll actually take you to schedule that appointment. So yeah, super cool. This link is actually available at, I'm not super sure what the link is. Give me 1 second. All right. But yeah, we do have an appointment. That's listed on our documentation page here, right? So just search that in our documentation page and you should be able to pull that up, okay? We also have monthly user meetings, right? So if you like any new information regarding like, any system updates or any kind of generalized questions you'd like to bring up to the entire community, then you can go ahead and join those too. Email us for a support or for like invites to that. And lastly, we have HPC tutorials, right? That are actually listed within our own kind of help page here, right? CISLucar.edu, of course, right? And yeah, there's some training documentation here that will cover basically everything we talked about today, as well as like a bunch of other additional topics, including Jupyter Hub. I know it's super popular. So yeah, if you want to take a peek at that, right? We'll be updating that for Derecho soon. And yeah, that'd be cool. Anyhow, lastly, best practices for answering tickets, right? If you like to answer tickets or if you like to pass along tickets to us, right, then please, pass us along the exact resource you're using with exact error messages, with your script location, right? And like any other kind of additional information like PBS job IDs or like any kind of paths where this all is. Okay. But yeah, I'll go ahead and close off from here. I know everyone's hungry for lunch. So yeah, hop off. We'll be here for questions just throughout the afternoon. All right, so if you have anything else, feel free to pop in and we'll be happy to answer you through like breakout sessions.
All right. Hey, thanks everyone who spoke this morning and thank you for all the questions. We appreciate it. We will, a lot of the conversation which happens these days is also on our in-car HPC user Slack channel. So please join there. A number of you already have seen a ton of new registrations since the RSVPs for this event came out. So really appreciate it. We are going to break for lunch. We do have a couple, I'd say prepared-ish items related to some of the questions we got if things head in that direction. But again, I'd encourage you to drop any questions that you have, you want more detail on in the chat, and then we will percolate on those over lunch and join at 1 o'clock, the top of the hour.